Hello. Okay, I think we can start. Um, Hi everyone. My name is Alexander Kryzhanovsky. I'm CEO and founder of Team PST Technologies. And basically, we do two types of development. The first one is we develop our own open source. Yeah? Definitely. Yeah, absolutely. Better? Okay, cool. Thank you. First one is our open source product. It's PSTFW. Basically, it's a hybrid of HTTP accelerator and a firewall built into the Linux TCP IP stack. The main focus of the product is performance and security, and the product is designed to fight against massive DDoS attacks. And we develop also proprietary modules around the open source engine. The primaries are volumetric DDoS mitigation based on XDP models and machine learning model to fight against web scraping bots. Also, we do custom projects for our clients, also in the area of high performance. For example, we contributed a lot into MariaDB and Percona servers. We develop NFS and S3 ultra-scalable storages in kernel bypass technologies, and WAFs and other security and networking stuff. In this talk, I'll be focusing on scalable and fast data structures. We face them in different areas. In Team PSTFW, in our projects for our clients. In Team PSTFW, since it's a HTTP accelerator, it works with web cache, and web cache is essentially in-memory database. So it's very important to have a scalable and fast web cache. Also for our clients, for example, for MariaDB, we did research for one of the problems with transaction handling hash table. I will talk about this problem in my slides. About Team PSTFW, most of this talk will be about our next version of index, which is still in proof of concept state. And there are many limitations and context about this web cache. The first is that it works in Linux TCP IP stack, so it's software queue context. You cannot sleep, and you can work, and you must work very fast. Specific accuracy should be taken about tail latency. For example, if we consider that every 10,000 requests requires 2 to 3 seconds to complete. It could be looks like very small problem. It's very rare condition. However, if you work on CDN and you have thousands of nodes, and each of the nodes processes 100,000 requests per second, it turns out that every second 10,000 of your clients may not see the hero images of your client websites. So it is crucial, but there are two conditions about tail latency. The first one is that it works on big numbers, so it appears on big numbers when you see a lot of traffic. And the second one is that usually it appears, and the most bad cases for tail latency occurs on very busy machines. When you experience the peak traffic, you get the tail latency. Speaking about the tail latency is important for this talk because data structures can contribute to tail latency. For example, if you do hash table rehashing and you do this under global lock, you definitely from time to time have a huge tail latency. Next, about data structures as a database. In our case, this is exactly our case. We work with shared data cache. There are approaches like Tarantul, when you have per CPU, per thread database shard. It doesn't work for us because we need a shared cache. Every CPU can process any request. We need a shared data structure. There are a lot of data, and if we would consider pure CPU shards, then we will need to resolve problem of proper load balancing, data movement among the CPU memories, and so on. So it's also not so easy problem to properly load balance among shards or solve the problem of shared data structure. Next thing is that we work for web cache. Web cache is mostly about data reads. There are a lot of insertions, especially when you just start. You have no data in your cache, and you also have a lot of insertions. Deletions typically happen on eviction when you're out of memory, and typically they can be not so efficient and not so frequent. As I said, TMPST web cache and the in-memory database, it's TMPST works in software queue context. It's essentially in-memory database, and we need some persistency. So if you have a planned shutdown of your web server, we can dump all the data to disk. But if some hard reset occurs, you lose the data. Some persistence is not a real durable database, but just some persistence. But the main things are about in memory. Next, we need to take care about duplicate cache entries. Web cache can store stale entries, so we have a duplicate keys inside the database. Next, we use the data structures not only for web cache, but also for other purposes, like filtration databases. For example, if we consider filtration databases, it could be just IPv4 addresses, 4 bytes, so you should be also efficient to store very small data items. And this interesting property is that large data like web entries, web objects, may have different sizes. From the other side, small objects like firewall rules or so on are fixed size. So we either have fixed size small objects or large varying size objects. A couple of words about log-free, wait-free, and what it is about. In our case, we have a log-free algorithm. It means that the whole system does progress. However, some CPUs may struggle to make progress or do no progress for some time. With wait-free algorithms, every worker must do some progress. It's harder to implement. The most problem with log-free algorithms, it might be hard, for example, to read and insert into the database concurrently from different CPUs. But real problems begins with data freeing, when you need to free some data which might be observed by some of the readers. And there are several approaches well known. One of them is reference counters. For example, in C++, you can use shared pointer, and you take care about the references, and this on the data structure user responsibility. The next one is read copy update. It's a mechanism come from the Linux kernel. If you need to update some data, you make a copy, insert it, and wait for grace period to make sure that no readers observe the old copy. And now you can free the data. Next one is hazard pointers. Bit different. You keep second helping pointer per CPU, and you can check the pointers. And also the dummy nodes. If you have data structure, you can introduce dummy nodes. The log-free release implementation with dummy nodes typically had a node which is always preserved in the data structure and never remove it. And this dummy nodes helps to handle removals. Let's have a look a bit more details about all the approaches. The first one is hazard pointers. We do use hazard pointers in our implementation. The main thing is that we have a slide about the code example for hazard pointer, but now just the key concepts and pros and cons for the approach. Hazard pointer keeps secondary per CPU or per thread local pointer, name it as hazard pointers. Every CPU which reads the data must set hazard pointer equal to the pointer stored in the data structure, and when updater needs to update the data, it must check that all the hazard pointers are invalid on all the CPUs. And if they are invalid, we can go and remove the data. The bad thing about the approach is that, well, good thing is that we work with per CPU data. It's much better than basic reference counters like a shared pointer, right? But the bad thing is that reads aren't cheap at all. We still need to make some reference counting. Next thing is that if you think about using hazard pointer for data structure itself, for example, we try to implement a linked list using hazard pointers, and each of the list nodes must use a hazard pointer to another node. We might find that this protocol will be very sophisticated. So typically hazard pointers works only for data itself, not for data structures. And typically hazard pointers work when you have only one, maybe two hazard pointers per time for each of the CPUs. Next, about read copy update. The very nice thing is that this is the fastest what you can have for read side, because read size is almost absolutely no operation. In some kernel builds, it's absolutely for free. And the thing is only on updaters. You need to make a copy, insert it, and when you remove the data, you need to wait for a grace period while all the readers will see the next version of the data. And probably on your Linux kernels, maybe last old Linux kernel builds, you might see a CU core, CU threads using a lot of CPUs. This is the thing that CPU need to wait for grace period and remove the data at once for long time removals. Another thing is that readers must be very quick. Since we need to wait for grace period, all readers must be very quick. And it works good only if we have very small number of updates or removals. Next thing is per CPU reference counters. There are no public good documentation, but there's only implementation inside the kernel. And basic idea is that we keep reference counters for each CPU. And once we need to update, we also collide to global counter. We move from per CPU counters to global and make operation with the counters. Not so good because we have to work with reference counters per CPU. It's slower than hazard pointers. From other side, updates is even worse than RCU. Anyway, there are a couple of good resources if you're interested in these approaches, pros and cons, and comparison with global reference counting. There are good talks with Paul McKinney and other authors, and paper which considers all the approaches. Next, move to data structures on their own. If we consider hash tables and trees, then hash tables are famous for fast point queries. So if you need to look for some particular key, they are blazingly fast, maybe the fastest data structure. However, typically, if you need to have a good hash table, you need to rehash your items. And rehashing, we still use some kind of rehashing in our data structure, but we try to get it at least scalable and as deterministic as possible. Trees from other side are good for range queries. For example, if you need to satisfy query, just like look all the keys with particular prefix. The trees are good. In hash table, you need to scan the whole hash table. However, trees typically need some rebalancing, also not so good operation, but it's probably more faster than for hash tables. The next data structure is trie, also known as prefix trie, Patricia trie, radix trie, and does not need rebalancing, but it must either do some compression or reorganization. We choose that data structure and try to make it as fast as possible. Let's just stop a little bit more about binary trees. If we compare binary trees with a hash table, binary tree is almost impossible to implement with per node log or log free. It's possible, they are still log, but it's very, very hard, and typically final results of the log aren't so performant. From the other side, hash tables are very easy to put log for each of the collision bucket, and it's easy to scale with hash tables. Hash tables typically much faster on multi-CPU. Next, about hash tables. Hash tables, typically we can define two types of hash tables. Open addressing, when all the items are stored in the hash table itself, and we need to reorganize the hash tables on insertion and resolve collisions inside the hash table. Another opportunity is to keep hash table, maybe from time to time make it larger, but resolve collisions inside the buckets. The most naive implementation is just a linked list for each of the collision buckets. It's easier to implement with granular locking per logs, and amazing opportunity for hash tables with open addressing is to use single instruction multiple data acceleration. There was a talk from Google hash table where the guys implemented single instruction multiple data and can scan all the keys in the hash table using the vector instructions. It's very fast, but typically this hash table works only for single thread implementation, not about log free or something like that. And has split ordered trees. That's the data structure example, which uses dummy nodes to help removals. The thing is that we, when we remove the node, we use dummy nodes. And as hash table grows, there are many more and more dummy nodes. And if you, for example, insert 1 billion items into the hash table, you have a lot of dummy nodes. And next, you remove all the billion nodes. And the empty hash table still has a lot of dummy nodes. And now, if you try to insert the next 1 billion items, you are very slow because of dummy nodes. So that was particularly the problem for MariaDB, which uses this approach. And another thing is that Intel thread building blocks library also has implementation of this type of hash tables. It's blazingly fast on lookup, on inserts, but very slow on removals. And moreover, you need to acquire global lock for removal. Next, about the trees and radix trees. Typically, we talk about two types of the trees. That could be prefix tree in case of string keys, or it could be radix tree in case of integer keys. On the left is an example for prefix tree. If we store a lot of text strings, we can get the common prefixes and branch only when the prefix starts to different, and we get the tree. The radix tree is one of the most used implementation. Is a page table in CPUs and operating system. On the right, there's virtual address mapping to physical addresses, and we use 4 or 5 level radix tree to map virtual addresses to physical. And in this case, we just take, we split the virtual address by portions of 9 bits, and each 9 bits address branch inside the particular level. So each of the levels, for example, global directory is essentially a physical page. It has 512, it's an array of 512 addresses, physical, and 512 is exactly 2 in power of 9. So we, with index of 9 bits, we can index resolve the particular level. The good thing about the radix tree is that it's constant height. No matter how many items do you store inside the tree, maybe 1 billion, but the height of the tree is constant, it's 4. It's an amazing, amazing property. Also, the algorithm just to take bits, resolve the address, is very easy. It's very easy to implement even in hardware. It's very scalable. It's easy to implement it log-free. Wonderful. The very big drawback of this data structure is that it's very memory hungry. Consider that we have only one virtual address, and we spent 4 system pages just for one address. Take one address with, think about it as a key, far from the first one, and you allocate 3 more pages to keep the mapping. So this is why when you do malloc in your programs, operating system returns your addresses as closer to each other to provide spatial locality and improve memory usage by page table. With thinking about the memory greedy for page tables, there are attempts to improve the memory usage by the table. One of them is Judy arrays. They provide several compression techniques. Unfortunately, it's not cache conscious, hard to make concurrent in that particular case. And basically, if we think about radix tree, we can think about it as levels of hash tables. And each hash table resolves hash values for particular 9 bits of the key. So we can define the 4 hash functions which take different parts of the key. So this is very, very common with hash tables. Another attempts for path compressions, this for prefix trees was taken, for example, if we have a array starting with the same prefix, there's no need to create index nodes for each of the character. We can create only one node for slash, block, slash, and keep the tree smaller. Another opportunity to compress tries is a bursting tree. So the idea is that we start from very small root node with essentially again as just a basic hash table using the prefix of the key. And once we insert the first item, we allocate some collision bucket, very small one, and we start to insert items. For some period, we have a very efficient data structure, just one small hash table, small buckets, and when collision happens in a bucket, we insert a new index node for the appropriate index and use another part of the key for the second level of the index. And now we reinsert all the bucket entries from the first bucket with the collision to the new buckets referenced by the new index node. This is very similar to rehashing in hash tables, right? The big difference is that in this case, we have, if we use big enough root node, we much faster at the beginning when we supposed to have a lot of collisions. And in each of this bucket, we have collisions in parallel. So we have reorganization of collision buckets in parallel. So this is much better than to rehash the whole table. And another thing is that so far we've been talking about radix tree, whether for integer keys, fixed size keys, or for text keys, it's prefix trees. If we mix this try structure with the hash table, so before insertion of text keys, we compute hash of the keys and use the try radix try to keep the nodes. We move to hash array mapped try, and this is what we actually do in our case. Next thing is that suppose we have a very efficient data structure. It's scalable. It can insert from 100 CPUs, 1,000 items in parallel. So far, so good. However, when you insert some data, you need to allocate the data items, right? And if you call the regular memory allocator, it definitely has some optimization, but you might stuck on memory allocation just to insert many data. So basically, when we talk about efficient insertion, especially efficient freeing, we should also consider efficient memory allocators. In our case, we intermix the data structure with memory allocation. We use a technique to compress pointers as a reference to such techniques. And we have several considerations about the spatial locality. For example, we do sequential access to page tables. If we consider index data structure, we for sure firstly access all the index nodes, and only after that we access the data nodes. So in this case, it makes sense to allocate and keep index nodes in one place and data nodes in another one to improve the cache locality and page cache in TLB. Also, if we in a collision bucket, it makes sense to store data as close to each other to scan the bucket as fast as possible. A good question could be, why do we keep index nodes separately? We know about intrusive lists, for example, in C++, in other languages, when you keep the index nodes and nodes of data structure with the resulting stored data. On the left is a scheme for elastic bouncy trees used by HA proxy, and this interesting data structure, which is hybrid of binary tree and linked list. Basically, it's a binary tree, unbalanced. It's also mixed with radix tree because each of the bit of the key is defines whether you go to the left or to the right inside the tree. So it's unbalanced. Nobody cares about balancing. And another nice property is that all the data is kept with index nodes. The thing is that in this picture we have a tree of 2 levels. So if you need a leaf, you need to make 2 cache access, cache line access. Since you keep data with index nodes, you definitely fetch different cache lines to access the last node. From other side, example is like B-tree or some data structure which is conscious about the using CPU caches. And if we keep keys resolved on particular level of the tree fit into cache line, we might get wider tree and get a smaller number of traversals for the key. So the key idea is that if your data structure is small, it's more efficient to keep data with index. If you work with very large data structure, you should care about fast index lookups, and it makes sense to keep index separately. I talked about cache conscious. We target x86-64. Don't take the numbers too seriously. That's just some numbers to estimate the difference between the cache sizes, access times, and so on. But basically, the most important thing is that we operate with cache lines with size of 64 bytes. Also, there is TLB cache, which is about only about 1,000 entries. So with SCaLE cache, you can address only about 4 megabytes of data. Also, there's NUMA, which is with the costly remote access, and also we work with system pages, which are 4 kilobytes in size. Next, we already saw page table, and if we consider binary tree, the blue one, and if we need to traverse to the green leaf, and now we are going to resolve the leaf. We have a pointer to the leaf. But essentially, if you out of your TLB cache, out of your caches, you have very large binary tree like STD map. Then you might find that just to resolve one level of the tree, you need to traverse the whole page table. It means that the tree lives in another tree. So you have a multiplication, like every pointer requires going through another tree. So we should care about small head of the tree. Next, think about x86-64 is that this architecture with strong memory ordering. There was a nice talk on CPPCon about taking advantage of strong memory ordering in concurrent data structures. So you can design and rely on the particular hardware properties in designing your concurrent data structure. The thing is that basically this architecture is totally ordered, and only one case when you might see like unexpected results, right? For example, if we consider 2 CPUs, we have 2 memory locality X and Y, initialize it to 0. We start, for example, we observe what's happened on CPU 1. We store 1 to memory X and read Y to register 1. If we observe 0 in register 1, it means that CPU 2 didn't do any progress, didn't store 1 to Y. And it means that CPU 2 will store the results later. And having this, after Y writing, CPU 2 will store result of X into register 2, which should have already 1. So expected to see either both of 0 or both locations on 1. But on this architecture, we might observe actually both of 0. So we also considered Intel transaction memory like several years ago, and the thing is that it could be very good to have, for example, binary tree and rebalance the tree inside the one hardware transaction. However, it wasn't possible because the transaction handling could work only with very simple transactions, and after finding some security issues, the technology is essentially dead. So there's no transaction memory. Some already said about cache-conscious data structure. TLB caches fit to one cache line, so far so good. There was a lot of research in cache-conscious data structures. There are several links to research papers, but in general, none of the research provide good log-free implementations. Next thing, partially already said about this, that you either have fixed size hash values, if in our case for web cache, or you have ordering. But the thing is that we can reuse the same data structure and just vary whether we store text keys with infinite length, and the tree can grow infinitely deep, or we store fixed size hash keys, but we don't have ordering. And the thing is that we work with real data, which comes to us from real-life clients, and means that we cannot use perfect hashing because we don't know keys distribution up front. Just to summarize what TempestDB is, it's log-free, it's using bursting hash try. We use embedded memory allocator for memory locality and log-free stuff. A map is used just for persistency. Partially, we use read copy updates, so we do copy internal nodes on updates, and we use hazard pointers to work with removals. And the thing about pointers stability. Well, if we have a collision bucket and consider that we have a small data record stored in data structure, it makes sense to keep the data right in collision bucket. For example, if it's IPv4 address, it's even cheaper to copy the IP address rather than to return pointer for the from the data structure lookup. From the other side, if we work with very large stored data, we need to keep pointers. And if you experience a collision inside the data structure, then you copy. You need to reorganize the bucket, copy bucket, and copy the data between the bucket. It means that if you would return pointer to the small record stored inside the bucket, and the data structure is going to be reorganized, the pointer can be invalid because the data items will be moved to another bucket. With pointer stability, we should we should consider two options: either to store small fixed size records and return them with copying, and we cannot work directly with the data. Or if we need to return pointers from data structure lookup, then we need to use indirection. So in collision bucket, we store only pointers and reorganize the pointers, but pointers are the same and point to the real data. A couple of words about the memory allocator. It's simple. We have 128 data shards. Each CPU works with local memory allocators. So we split the whole file to 2 megabyte extents, and each CPU for large data works with its local per CPU extent. For small records, we can share the same extent between the CPUs. Next, each CPU has basically 3 pointers. The first one is index pointer. It's a offset for the current page used to allocate index nodes. And another for data page, the system page used to allocate bucket and memory for stored data. The free list is when we reclaim bucket or stored data, we put it to free list. It's just a linked list per CPU. We use the linked list nodes right inside the item. So it's also per CPU. So basically, all the CPU work with, in most of the time, with local data, and only when extent is exceeded, we need to allocate a new extent, and now we have some contention. Let's consider how the tree is organized. Consider that we have a root node with 16 items, and we use 4 bits from the key. We have a string foo, which was hashed. We have a hash value of 64 bits. We use last 4 bits as an index in the array of 16 offsets. 16 offsets of and each offset is 4 bytes, and now we have exactly 64 bytes. So each index node is exactly one cache line. Next, with each of the offset, we reserve 1 bit as a flag, whether the current index node is the last one, and it means that the current offset in this current offset points to the data node, or it's points to the index node, another one. So this is why we get 128 gigabyte limits. It's just 31 bit offset, and we offset defines index of 64 bytes within our memory allocator. Yeah, one thing is that to improve insertion time, especially when we start, 16 slots definitely not enough. So if you have like 100 CPUs, we start to concurrently insert a lot of data, we have huge collisions, especially on hash function. So in our implementation, we allow to specify how many bits you use to resolve on the first level. Like it could be any multiplication of 4 bits, like 8, 12, 16, and more. Next, we have each collision bucket has a header. And with header, we maintain a bitmap of occupied collision slots. Each slot is described with 2 bits, and the bits are used not only for occupied or free, but also for write in progress and remove in progress. The thing is that once we insert, imagine that you fetch large web objects from upstream, like maybe several gigabytes. You'll be writing the parts of the objects into the cache during some period of time. So you need some flag to indicate that this object is in progress of writing. And the same with removal. We also have might have concurrent removals, so we use this flag also to handle concurrent removals and bucket reorganization. And next, when we fetch it, when we try to insert our key into the hash table, we allocate a new bucket. And within the bucket, we try to make atomic compare exchange on bitmap. Our architecture allows atomic bit operations, and we can acquire particular bits in lock-free manner. Next, when we have no data records in our tree. In our case, we descant in the tree. We have a look into the slot, which corresponds to the current part of hash value, and we start from creation a new bucket and write data into the bucket. So we have a current tree, and somewhere outside we build the data and bucket which we are going to insert. After that, we also do atomic compare exchange on index node and replace offset to the current bucket. If we, during compare exchange, find that somebody already written some offset to this index node, then it means that we have a collision. We remove the bucket and retry the operation. And this time we will observe the bucket where we can move to collision inside the bucket. Next, if we have large data to insert, we basically do the same. We just allocate new bucket, we allocate data, large data, write the data what we have at least, and try to insert the bucket into the tree. And if we fail in this collision, we don't need to free the whole data, but we free only the bucket. Next collision happened. We, for example, bucket can contain only 3 items, but we try to insert the 4th one. We experience collision, and in this case, we have a bad situation when the next 4 bits for the next index level also have a collision. So what we do? Inside the loop, we fail on our compare exchange on index. We allocate a new index node, we allocate a new bucket, and try to insert data from old bucket to the new buckets. And now we really build one level of index tree separately, maybe more trees, buckets, and data. So essentially, we build a whole subtree outside of the main tree, which is observed by current readers and other updaters. Once we are done with insertion, we think that at the moment we have no any insertions inside the bucket. And now we try to compare and exchange the collision map in old bucket with a new bucket which we got from reservation. For example, several records were moved from one bucket to another. If we find that we see the same collision map as we saw before starting to build the new subtree, we're good and we can replace. If we found that the bucket has changed, we just drop all the buckets and retry the operation. It's costly, but it's concurrent. So as we saw, we mix copying. We extensively copy data, index nodes, buckets, and data. And this was some kind of CU approach. But for removal, we use hazard pointers. The thing is that we return, when we provide API for this data structure, we return not the final record which we found in data structure, but we return the whole bucket. The reason for this is that we have no idea about the semantics of stored data. We have no access to the keys. The user computed the hash value of the key, inserted the data, but the key is essentially a URL of a page host. It resides in the inside the stored item, and when we had a cache lookup, we have to observe all the collisions. For the same URL, we might have different versions of web page. That's why we need keys collision. So it means that during some time, user can traverse the bucket, and it means that we take hazard pointer for some time. We cannot use CU. So we can just quickly scan the bucket and return the pointer. We need the bucket to traverse it for collision. One downside of this approach is that when we remove some data from the bucket, we need to copy the bucket and replace the old bucket with a new one. So if we experience out of memory, we started cache eviction thread, and now it requires some memory to free memory, right? So in this case, we need to preserve some percentage of memory for being able to allocate buckets. In this code sample, we have a hazard pointer implementation. In our case, we just have an offset for active bucket. It's offset, not a pointer, but essentially this is just the same, looks like and smells like a hazard pointer. We descan the tree, get the bucket pointer. Next, we call the function tbh try get bucket, which is essentially writes the per CPU hazard pointer with the bucket pointer, and next step we compare the retrieved pointer with actual pointer stored in the current index tree. If they're equal, we return the bucket address. So we successfully established hazard pointer. If not, we repeat the operation, just a basic hazard pointer. On remove side, this is just a pseudocode. We copy bucket, we do components exchange with collision map, and we need to traverse all the per CPU hazard pointers, active buckets, to see that whether there is no CPU observing the bucket pointer which we're going to delete. If we don't see the bucket, we already exchanged, places the new bucket pointer into the index, publishes it, and now if we traverse all the CPUs and don't see the same bucket pointer in hazard pointer, then we can make progress. So that's pretty all what I had. Team PSTW is available in GitHub, and also the current development of the proof of concept in our separate repo is just proof of concept. And now I'm ready for your questions. So thank you. Yeah.
Do you have any problems with data skew with your keys? Like because a lot of it was URL paths, right? So I was wondering if that caused problems for your cache.
Sorry, I didn't get.
Data skew, like you have a whole bunch of keys that all have a very similar prefix.
Yeah.
And it's like a distortion in the distribution, making the tree try a little bit unbalanced.
We use a hash function, so we don't use. Yeah, but basically in our current implementation we use very simple hash function, and moreover in any hash function it's not a cryptographic function, so we can find the right hash collision. And there are DDoS attacks targeting like random URLs. So in this case we just rate limit for error codes from upstream. So we don't try to fight with attack on the cache, but we target 404 responses for rate limit from backend. So in our approach in DDoS mitigation, we care about upstream stress. It means like error pages, response time, and so on. We account the performance metrics, and we observe if backend in stress condition, then we can rate limit the users involving requests to the substream. So it's different level. Yeah. But thank you. That's quite interesting question about the hash securities. Yeah. Any more questions? Okay, then thank you so much.
I should now. It looks like you just turned it on.
It does look like you just turned it on.
Is it that one? Test 1, 2.
Awesome. Thank you.
Oh yeah. We're gonna wait. We're gonna let's introduce you properly. You wanna?
Yeah, I can maybe do. I think
Go for it.
yeah. If you want to use the headset.
No, I'm totally fine.
Okay.
Yeah.
Mostly because that will be good for questions, so they can hear your questions. So
Oh wait.
Actually,
Are you actually up?
I am up next in 5 minutes.
yeah.
I need Franklin to use the bathroom.
Okay.
Yeah. Do you?
Before the talk starts, I may as well tell you guys what this is here. I don't know if you've ever played the game Mario Maker 2 on the Nintendo Switch. That is a visualization of replays for a speedrun mode in that game. Just segue into why I like APIs so much, why I like data, and what sorts of interesting things it can enable. Yeah, you can. Oh, what's a speed run? Well, yeah, it's a competition to beat a game quickly but it's hard to overstate what is required to beat a game quickly. It's not just having good reflexes, it's also knowing the game like you know the back of your hands. You have to treat it like it's a piece of software you're exploiting. And you can probably guess what my background is now. Of course. So yeah, my name is Addison, and I'm here to present about my perspective on how to create APIs as a reverse engineer. So I come from Colorado, and I went to university at the Colorado School of Mines, and I presented talks at the Linux users group there. And I have presented 10 talks, but I've since graduated. And I'm a hobbyist reverse engineer with experience in geospatial APIs, transit, and video game APIs. And I'm also a data scientist from school. I have a data science degree. So one of my interests in that space is I really enjoy creating custom clients for APIs. Like, for example, my most popular API is the public Mario Maker 2 API, which players use to get metadata about levels and also level files themselves so that they can render them and use them to play the game. So why should you care about making an API really good and treating it as a completely different thing to improve as a part of your service? I think that APIs are the primary way both non-human consumers use your service. For example, AI scrapers, we may not like them, but some services could really, we have to cater towards AI scrapers, it feels like nowadays. And we also have to cater towards other services, like, for example, bots that monitor the uptime of a service. You need an API that's capable of serving data to those bots that will be querying constantly. But also, human consumers use your service through alternative means, and that comes from my background as a reverse engineer making custom clients. People sometimes use your service in a way you don't expect. And also, it gives your service more reach than otherwise possible. Sometimes the front end that you create is not the one that your users are looking for. Maybe it's not fast enough for them, or maybe it doesn't have the automation tools that they require. And I think some clever examples of tools that show the flexibility of allowing an API to have this much information exposed is Steam Database is used by both developers and gamers. Gamers to see what games are popular, but also developers to gauge trends in the industry. And 50,000 websites use Twitter embeds, and the Twitter embed is only possible because of a very good free system that developers can use to have access to Twitter tweets. And Terraform is an infrastructure as code platform. It has 1 billion+ downloads, and it is primarily just a custom client for cloud APIs, for cloud providers. I've used the Google Cloud Platform UI. It is the only website that lags my MacBook M1. So Terraform is kind of a godsend in that way. I need the APIs because the front end provided by Google is not sufficient for me. So what makes a great API? I distilled it down into 4 data points. So latency, the speed of the API; quantity, the amount of data that an endpoint provides; coverage, the total coverage of all the endpoints in relative to your service; and the quality of the API in general. And the way that I depict coverage here is coverage is just what amount of your service is covered by some sort of data source. Are there parts of your service that don't have a public API that people can't use to do things? And quantity is just, is your endpoint capable of serving as almost everything that your service provides on that particular topic? So latency, serving users fast with minimal overhead. Minimal overhead in this means you don't want to, cause your server to burst into flames. You want to be able to serve people quickly, but not at the not at the expense of your own hardware. So this may or may not load, but I reverse engineered Baidu Maps, which is a really popular mapping platform in China, and it basically is the analog for Google Maps here. And I was extremely surprised to find that, frankly, it is slow. That right there is the actual realistic raw speed of the Baidu Maps front end. Even if you operate it just as you would with the exact same interface as Google Maps, in fact, even more restrictive, Google Maps is doing more here, it's still much slower. And imagine being on the road trying to determine how to get from an airport to your hotel, and your mapping platform takes that long. But then information changes. Suddenly, you find out there's a detour, so you can't take a major bridge. That means that bus is no longer usable. But wait a minute, Baidu Maps takes like 10 seconds to determine that information. It's simply too slow for users. And another example of this is, in addition to custom clients, I make custom servers for things. So I made a custom server that replicated the API of Mario Maker 2, so you can connect to my server with a modded switch directly. And the API I designed was designed precisely so these exact endpoints are fast. I didn't design it for ease of use for development. For my own use, I designed it so that people would be able to use my service quickly. So I have these somewhat complicated queries, but I created an index so that those queries would be fast, because at the end of the day, what matters is the actual latency of the endpoints themselves. Your users don't really care what the quality of your backend is. They care whether things are fast. And another example of this, this is just a query that will give you, this is the original graphic that I had at the beginning of the talk was a visualization of a bunch of replays. These are the replays. And the request for them, which mirrors what Nintendo does, is this sort of union against times that are slightly slower and times that are slightly faster. But I need an index that makes that quick, because that's what my users are using. They want that data. And this is 2 examples of code that one of them seems pretty reasonable. I'm trying to get a world record. A world record is simply the smallest value in a table. So let's do an order by with a limit 1. Wow, we did it. We did it. No, we didn't do it. Let's make this super advanced code. Like, the code on the left there is a system that finds the current record owner, which has a flag that says is world record, desets it or deselects it, and then sets it on the new world record. That seems like a bunch of extra computation if I just want the world record. But I don't just want the world record. There we go. I need the number of world records that a player has. And imagine the amount of computation required to get a list of all the levels that somebody has played, and then get their time, their rank in that level, and determine whether it's a world record. We're dealing with basically like kind of O of n versus O of n times m is more of a correct analog. So that extra complexity was worth it because it sped up the endpoints that users are actually using. And unfortunately, if you're going to make things fast, that means certain malicious users need to be restricted from making requests quickly, because that's the basis for a DDoS, and DDoSs are an absolute bane of our existence. So sometimes clever engineering is not enough. I can create an architecture with very good caching and very good data structures, but at the end of the day, there are billions of people on Earth, and there's like millions of machines that could, in fact, try to slow down my service. So try to, of course, implement some system that will eventually just say no to a request. The way that I do that for my API is a semaphore system. So I have a semaphore that's set to 4. 4 people worldwide are allowed to make requests. That's pretty reasonable. My system has the additional problem that I don't want to overload Nintendo. So there's actually two users to please, my users and Nintendo themselves. So my way of satisfying that was simply a semaphore. And I think that APIs that are extremely fast are not just useful and convenient for people, but they enable entirely new avenues of discovery for using data. So an example of the top right message was, I released a endpoint that would return Ninja times for this speedrun mode. And a few days after I did that, there was a new Ninja that released for the game. And originally, people were submitting their times onto a spreadsheet that they had played. So there were ranks that people didn't know anything about. But if you have an endpoint that's fast and will give you that data essentially live, then you can get a live feed of world records, which was a really cool moment because people were tracking the world records second by second. And that was a really exciting few hours as people watched as the record went down and down and down. And I think that certain products, like Google Takeout, for example, Google Takeout is not designed to be a live feed, and that's intentional. It's one of the best ways to get access to things like YouTube data if you want to do like analytics on a user and give them recommendations, but it's not live. It's delayed by a day, which significantly reduces its usability for a number of different possible use cases. And this is true of, I think, a number of us, is that we have this sort of exponential curve of users. We have some users who make a lot of requests, a lot of users who make very few requests. And in certain cases, you can trust someone and you can give them special exemptions to your service. So you can remove the rate limit on them. So there's a user who created a level viewer for my API, and I gave them a special exemption to the rate limit because I trust them. In fact, they're much older than me. They've been in this industry for longer. So I know that they make good decisions about architecture, and they're not going to overload my API. So, and quantity. So providing as much data as possible of some type over each endpoint. So an example for Mario Maker 2 is, unfortunately, and I know this, they only return the last 1,000 comments for each level, which that's because in-game, that's the number of comments you can view. But I know, because they return it as a field on one of their level info endpoints, that there's 133,000 comments. So more than 99% of the data that was created and uploaded to this service is no longer accessible. And sure, this is just Mario Maker 2 comments, but I would be somewhat annoyed if data that I uploaded to a service became inaccessible after like a few years. That's kind of an insult. So in cases like this, surely there's a better way that we can provide more information. We don't need to limit ourselves. And an obvious solution to that is pagination. So pagination is pretty simple because it creates this system that both rewards users, users who don't need your API that much, and users who use your API quite a bit. You have users who don't want 1,000 comments at once. So if they make that request, they want it to be quick because what they're really looking for is maybe just 3 comments, just a smattering, an example of what the API produces. But some other people, like me, of course, want all the data, and both of us can be happy. Just one of us can trade off convenience and time for that data. So I'm willing to spend more time as long as you give me an option to get more data, and that's what pagination enables. Just simply page 1, page 2, page 3. And another example of this is something like Whois. Whois is super popular for just normal people who just want to see, people who want to know where their requests are going to maybe gauge latency for example, like running a trace route or something. All I want to know is just to see if there's a performance regression because of some particular aspect of my IP. But there's also people who want to run like trends and analysis on those IPs. And a service like Whois, this is the American, it's Aaron.net. Like Aaron provides a system that allows you to do a single lookup and a bulk lookup. So both people are happy. Because this use case is significantly different from the creating a map of the internet use case. And yet, truly both of those are valid. This gives us important information to know, like, what is the internet being used for? And I think that's pretty valuable. It's good to know, because we know that the IPv4 pool is going to be exhausted soon. It's good to know, like, why and how that's going to happen. And both of these services are equally valid. And this was an example I just finished recently, but I scraped, if you guys know anything about the Wii U or 3DS, those online services were shut down last year, and we had a few months to prepare for that. Well, I decided to scrape the entire service, every single game. It's somewhere in the realm of like 300 games that I downloaded, basically all the data they exposed. And the reason I wanted to do that is I believe it's digital archaeology to save information like this. But the technical details of how I did this, especially for leaderboards, is I used a form of pagination in order to obtain that data. And of course, people who play Angry Birds, they only care what the top 10 times are. They care what the world records are. But by using their API in such a way, I was basically able to paginate through the rest of the records, which creates interesting opportunities for data analysis and just gauging popular games. And it's an interesting avenue. And this is a world record chart, which I think is pretty cool. And quantity is also useful if you somehow provide some sort of cross-reference to another service. So this example here is this endpoint. In-game, people really only care about this endpoint to get just like world records, their rank, and also get a number of replay times around them. But because of the this right here, the player ID, which is this really extensible ID used all across Nintendo, I was able to completely scrape this entire service and create an interesting little map, which was not what the API was designed for, but it was made possible because there was this simple ID that I knew would work across the API. And yeah, this is 133,000 players, which is why it looks like a fluid simulation. So another example of quantity is progressive loading. So maybe you just have a few small pieces of data, but they have extremely high resolution. And the classic example of this is Google Maps. It's not just there in the tiling system of its, in the way that it serves its map, but it's also there in the way that it serves Street View data. So I reverse engineered Google Street View and made a custom client for it. And what I learned when I did that is that they use a resolution system. You can see this when you use Google Maps. You'll plop down the little yellow man, and it'll take like a solid 30 seconds for it to load at full resolution. And that's a clever design choice, because maybe I only want to see what color the grass is. But if I wait 30 seconds, once again the trade-off for time versus data, then I can see the whole picture at the highest source resolution. So coverage. How well does your API cover the use cases of your service? So an example like Baidu Maps. I found that Baidu Maps is, and this is my shade section of the talk against Baidu Maps, which is why I'm not in China right now, is that it does an exceptionally poor job of giving me real on-the-ground directions. The only real data that it gives me is the train that I'm going to take. It's a very weird design decision where it doesn't give you point-to-point directions. It just gives you the main train that you're going to use, and then it gives you, it says, you can take a taxi to the train station. And I'm like, no, I'm not doing that. And I know for a fact Baidu Maps has access to this data because they do on mobile. They do in the app, they have access to this. But in the browser, they chose to deliberately reduce what data was accessible to the user. And what if I have my laptop on the train and I want to know how to get from my train station to my hotel? I'm not interested in downloading the app for many different reasons as a US citizen, but, but I'm not interested in downloading the app. So why would the API deliberately change what coverage of the service it provides depending on the platform? And in the example of Baidu Maps, in order to recreate the Google demo I showed at the beginning of the talk, I had to reverse engineer 2 additional apps. 3 times the amount of work for me? And also cases like accommodating new use cases, because you as the developer can't anticipate what sort of uses people are going to find out of your platform. So try to make it extensible enough that you can insert new endpoints that people request over time. And the way that that worked for me is gaming is a Discord native kind of thing. So people ping me and ping me and ping me all the time about various things they want added to the API. And over time, I add those features to the API. And one important thing is try not to deprecate your endpoints, because some developers are just slower moving than other developers. They might miss the fact that you deprecated. Yes, I know that versioning is this incremental system where you warn people about a deprecation before it happens, and you provide alternative ways to continue using the service. But in general, it's just a really nice bit of convenience for users when they can reliably know that an endpoint will exist for a long time. And also simplifying existing endpoints. Sometimes you made bad decisions. And sometimes you shouldn't deprecate, but it would be really nice if you maybe fixed up your mistakes. And also just the quality of an API, because I believe that a good API enables new creative emergent uses of your service. And especially if you're the kind of service that people use for fun, which is why an example I used at the beginning was Steam database, people will find that they have new interesting reasons to have access to that data. And I think it really, it inspires people when they have access to that data well. So interoperability is something I talked about before, but if you expose global UIDs that are compatible with other APIs, then you can create a whole web of data. And sometimes one global UID opens up an entire avenue of experimentation. And an example in Baidu Maps was, well, the example in Baidu Maps is that there was no global UID. Really a shame. Nothing at all matches. The format of the name of a bus line changes. The numerical ID for a bus line changes. It's kind of unbelievable. But an API that does this well will create a lot of cool opportunities. Like if Baidu Maps had worked here, then I would have been able to properly recreate the functionality of Google Maps, which I did eventually do with a lot of string parsing, a lot of ad hoc string parsing. But if Baidu Maps did this properly, I wouldn't need to do that. And examples of good global UIDs you've definitely heard of is ISBN is not intended, of course, global UIDs aren't really human readable, but that's why we're at a Linux conference, so it's really nice to have computer readable stuff everywhere. And it's just a simple barcode that really enables you to do quite a lot of cool things, like learning whether a book that you really like is being archived forever by the Library of Congress. Or, making your own stock trading platform, but you want to add Apple there. Well, what's Apple's ticker symbol? And I'd say that the biggest API should probably become the global UID or some sort of meeting group that standardizes these things. Regardless, somebody should step up and become the global UID because competing standards aren't fun. And also, it's nice when an API is self-documenting, and that's really just not just are things interoperable, but are they obviously interoperable? So try to keep your naming consistent. In the case of Nintendo, I had to do the naming myself because I'm reverse engineering binary files. But for the public API that users use, I have very consistent naming schemes that people know that a data ID always refers to a level as a numerical ID. And also try to ensure that they take the same domain. It's really a shame when you learn that there's an undocumented portion of the ID space that is not accessible by that endpoint but is accessible by another. It's just not fun. And also, it's nice to have the right data format. This is just a surprising thing that I noticed in the Baidu Maps API. They serve encrypted payloads in base 64. However, and this is giving away my secrets, I simply took the encrypted out of the URL and it became plain text. Oh my goodness. I was like, thank you, engineer. I don't know why you did that, but you saved my life. But this is not just like a weird attempt at security, but it's also just extremely slow. Like, why are we turning this encrypted, like, base 64 payload into, like, a binary file? Okay, it did end up becoming JSON, to be fair, but, like, if you're going to do that anyway, encrypt a protobuffer and send it to me instead. It would have been harder for me as a reverse engineer, but I would have understood that decision a lot more than what they went with. And yeah, just use well-accepted standards because the way that you send data is not just for usability, but it's also for performance, really. And yeah, when the data format isn't right, a reverse engineer will make a new one. Because that's what I did for the Mario API. Basically, all the data that I expose is a recreated standard that I didn't agree with. And even examples that go as far back as the format used for NES emulators. The ROM format people use, that's a reverse engineered, recreated format that has now become the standard. Because just give your users what they want, really. And also you want to do logging, because this was an interesting case where I had a user who made a lot of requests, 1.5 gigabytes over like a week requests, to this endpoint that is giving you multiple level infos for if you provide just a list of comma-separated level IDs. And what I learned is that this was a replacement for my inability, or my the fact that I didn't add an endpoint for multiple users, because there's a fixed part of level info that doesn't change. It's the person who first beat the level, because you can never beat the level first again. So they were treating it as a multiple user endpoint. The reason why is they wanted a tiny little leaderboard because they were trying to basically just track how they were doing against their friends. It was kind of cute. But they were creating a new endpoint because of my inability to create one. And I only caught that because I was logging and asked questions. And also having example code, obviously. And not just having example code, but showing the different ways in which people might use your API. Because sometimes people are starting a new project, or your API is, your client code is really all-encompassing and does a lot of encryption, for example. People will want to use whatever client library you provide. But sometimes people have frameworks they've created, and your client APIs don't really work with their frameworks. So providing example code for both situations is very nice. And yeah, this code is identical. And also, of course, having good documentation, which is its own talk. But the way that I see it is you can fail to say a lot of things, but you really should say like what the domain of your endpoint is. For example, my API has quite a few enums, but that's intentional. That's a performance decision because it saves nanoseconds in the case where you're only trying to parse something very particular. So I provided a list of enums for people to use, and it's just a great performance improvement. And also linking to external documentation when using a standardized format is really nice. Don't have people try to determine your format from scratch. Even an anecdotal story about this is the case of I tried to fine-tune a private large language model for a school class, and I found that the format for the JSON file for fine-tuning is just difficult to find online. And I was just kind of in awe of the fact that none of these projects mentioned what the data format was. I really wanted to use their API, but they didn't document how to use it. You want things to be compatible for a long time. You don't really want to deprecate things. So maybe you could add endpoint prefixes, which is really common. You see v1 all the time. But also backwards compatibility is really nice. And yeah, advertise changes when you make them, and try to choose good UIDs at the beginning because people will probably be saving those UIDs in their own database. So you don't want to basically make a dead UID for them. That would be a shame. And the way I did that is in the blog post that I documented my Google Street View reverse engineering, I reported that an endpoint on Google's side had changed. Of course, this is reverse engineering we're talking about. This is a private API, so Google doesn't really need to report that. But it's just nice to tell people when things change. And I have a section on the APIs I think are done right. Like GitHub is a really popular example. And their requests are made using GraphQL, which is extremely powerful and fixes quite a few of the problems described in this talk simply because of how powerful it is. But it also enables a lot of abuse of your API. It's a very finicky thing. But it's nice that they have a webhook API that triggers whenever you make a pull request or make a commit. That is a really useful live feature for users to use. And also they have pagination because it's GraphQL, which is a good example of how to handle quantity. They have a lot of endpoints, quite a few, just an unimaginable amount. You can get, there's an endpoint for the emojis you can use in pull requests, which is, and you know, on the discussion page, which is really funny. And also they provide a lot of example code for both curl and JavaScript, which is the example of having code for both a raw network request and the client library. And Hacker News is another good example of that, and they're very open about this. They advertise their API as being a dump of their in-memory data structures, which is an amount of freedom that a reverse engineer can only dream of, really. And yeah, they're extremely fast API. The amount of data is not extreme, but it's clear that this was a bunch of developers who really cared about the users of their API, so they made it very fast, and also payloads are very small. And they also provide this public incrementing ID that you can use to walk backwards through every post ever made, which is just an amazing example of quantity. And I know it's bad practice to have a public ID that's simply incrementing, but in cases where that data is not sensitive, it's extremely nice to have all of it. And also they prefix endpoints to preserve compatibility. And on the right here is a custom client for Hacker News that just shows that their API is so good that someone remade their entire client, which is just a standard of quality, really, for an API. And also, OpenStreetMap is a really exceptional example of an API. They have really good latency by providing bulk downloads of their entire data set. So you don't even need to depend on them anymore. You can download just a huge tar file of everything they own, and then they give you the libraries to process that data. So it's more an example of a data set. But where OpenStreetMap shines is they're not just a data set provider. They have a good blend of both bulk downloads and individual downloads, like reverse geocoding. They also, yeah, that's quantity. And coverage, they are comprehensive enough to replace Google Maps, and some users do that. For example, Wikipedia uses OpenStreetMap as their way of showing places. And that means they don't need to pay for some license from Google. So OpenStreetMap is serving a really important purpose here. And also they're extremely high quality because they have high compatibility with existing software. They basically follow all the standards. They also invent most of the standards. They're like, that's why people talk about OpenStreetMap even if they're using Google Maps. It's because the standards OpenStreetMap created are the ones Google Maps adopted. And also they have a very large active volunteer network. These are people who are having fun contributing to an API. And, you know, if that isn't a standard of quality for an API, then I don't know what is. And just two examples of APIs that are really just on extreme opposites. But on the left, this is the official Mario Kart 8 Deluxe record speedrun leaderboard. And this is what users actually use to determine whether they got a world record. It's a really exciting service because speedrunners are constantly watching this leaderboard to see who's currently in possession of the record, and it leads to some really just exciting moments. And this data was obtained by accessing the Nintendo API. And they also expose this data to other people. So it's just an API that encourages people to have fun with video game data. And also this on the right is just like a coverage map for a telecom company. And you're not looking at this to have fun. You're looking at this because your phone is not working and you need to call home right now. But luckily, this service is extremely easy to access. You can just Google like coverage map and it'll give you cell by cell. And the cells here, this is DIA, Denver International Airport. I'm from Denver. These cells are probably in the realm of like 10 meters by 10 meters, extremely granular data. And that'll really tell you immediately how good your internet actually is. And they easily could have made a shortcut and said, oh, Denver's working. And it's like, really? Well, it's not for me. Where does Denver start? I'm in DIA. DIA is like 10 miles outside of Denver. Is that still Denver? No, they give you a map that'll give you extremely granular data points. And that is the talk. These are my sources.
Thank you so much for the great talk. Yeah.
Yeah, check out my other work if you would like. Yeah.
So let's say I wanted to
Go for it.
have an API that was typical for reverse engineering. Should I basically follow your guidelines and reverse?
Well, the absolute easiest way, and this does not stop my colleagues who are much smarter than me, but encryption everywhere. Because I know that I'm maybe the opposite of most developers. I'm on both sides. I love to make APIs, but I also love to abuse them. But I can tell you that encryption will scare away most people. Really quality encryption will be unbreakable, and that's when you have a bug bounty program. If you're willing to pay $1 million to someone because they broke your API, then you've succeeded.
Real quick. I'm a web developer. I run a SaaS company, and we deal with, we integrate with a lot of public APIs, mostly email platforms. One of my pet peeves is over the years, I've realized I've watched APIs get chattier. Like taking ActiveCampaign, for instance, which is the email platform. You used to be able to, there was an endpoint that says, hey, for this email address, add this tag to it, right? It was one API endpoint, took two things and did it. And would just return okay or no or whatever.
Extremely simple, yep.
Right. But what I've noticed is that like ActiveCampaign and all the other ones are moving towards a more chatty API where like I first need to call to get the user ID, then I need to call to get the tag ID. If the tag ID doesn't exist, I have to call again to create the tag, get the ID, and then I have to make a final call to marry the tag ID and the user ID together. And I've just noticed this across the board on all these services, and I just wonder, why do you think you're doing that? Because they're clearly intentionally doing it. Is it laziness? Is it, I don't know, like what's the upswing to that?
I almost feel like there's two things. One of them is a good user practice. The other feels intentionally hostile. One of them, I'd say, is perhaps all of this is because they have a tree of APIs that depends on different IDs, and this is a performance improvement. If you save the ID that you got halfway down in the tree, then you can make requests to the bottom level of the tree multiple times without redoing the whole process. I can see the benefit of that. But I think the user hostile side is, I said that I really like when APIs are both usable from client libraries and
2012. In 2012, the Software Sustainability Institute was meeting at Oxford, and they were discussing things. And one of the things that they were discussing was this: how is it possible that nowadays there's no career path for software developers in academia? How do you do software development in academia? There's no such thing. There's no career path. So as people were discussing this, they realized that maybe the first step was, okay, let's recognize the people who develop software in academia. Let's see who they are. We don't even know. Are you developing software? I don't know. So what they did was they accessed the job postings. There's a centralized system in UK for academic job posting, and they look at software-oriented job titles in academia. And they found there were under 94 job titles. There were software-oriented job titles, or people in these roles were essentially saying, actually, what I'm doing, I have this role, but what I'm doing developing software. So the first step in 2012 was, okay, we need to be under the same banner. We need to push, because if we want to have a career progression, if we want to have a trajectory, if we want recognition, then we need to have a name. And that's how a unified name is. That's why the research software engineering word was coined, is to bring all these people together under the same umbrella, so that together we can define career progression for us, we can define or realign incentives in academia. So what's a research software engineer? Well, at the beginning, the theory was quite simple. You have software engineer on one side, you have researcher on one side, and then in the liminal space between software engineering and researcher, that's where research software engineer are. But then, as people started thinking about this a little bit more, they realized, actually, it's a little more nuanced than this. There is maybe traditional IT support, people that help us with Slurm, with high-performance computing, things like this. Those are using their skills to help us doing research. Are they research software engineer? Are they not research software engineer? And as time moves on, there's more and more recognition that research software engineer is not that simple. It's not your year in between. There is a lot of nuance in this. You can be a research software engineer if you're using your technical skills to help people find literature for your topic, for example. So the definition that I think we kind of settle on, and I personally like, it's a very general definition, and it's a definition that says that research software engineering are those who regularly use expertise in programming to advance research. So it's very broad, so you can be a research software engineer. Maybe you didn't even know. If you're the person helping your group with where you're computing, or if you're the code wizard, then you're a software engineer, a research software engineer. So now that we have a definition, we can go back to our timeline and see what happened from 2010 or 2012, move on. And I think what happened was that everything happened very quickly. In just 10 years, we moved from, well, Software Sustainability Institute was founded. We had the name Research Software Engineer. In 2014, professional society in UK, the Research Software Engineering Society was founded. In 2015, institutional founder, the Society of Engineers, gave money institutionally to support this. In 2016, there was the first conference with hundreds of people, all that were identified themselves as research software engineer. In 2018, we had the US RSC that was funded. the American version. It took me a while, but it's an American flag. I didn't recognize that. And now in 2021, now there is even a international research software engineer. Because what happened in the space of just 10 years is we moved from a bunch of people in Edinburgh to an international movement with lots of members and in many countries. So you can see the spread of societies that were founded in the past 10 years and that are bringing this idea of research software engineer in the world. And as you can see, in the same way we're trying to bring people on the same umbrella, on the same banner of research software engineer, all these societies, except the Swiss for some reason, decided to follow the same branding and the same line of using your purple, this, I don't know, question mark type of thing. So we're all together. We are a movement trying to change the system. But what are these societies doing? And I think the most important thing that societies are doing is bringing people together. Societies are bringing people together who believe that better software leads to better research. And this is massive, I think. During my PhD, I had no idea such a thing existed. I felt isolated. I felt no one cared about quality of research software. I was just, I care, but I'm the only weird person that wants to do this. No one around me cares about this. And there's many people like me. There's many people out there who believe that if we want to do better science, we must do better software. And these are the people that join these societies. And these societies, what they do is they build community. And the value of community is insane. So what societies are doing is, one, building community. Two, they're doing advocacy, because it's us, but then we're trying to change the system. A system that in Oxford is 1,000 years old. How do we do that? We need to group together. We need to show that what we're doing is important. And then societies are also providing training on so many levels. Technical training, like how you package your Python code, or training like how you start an RSC group. How do you find people like you? All sorts of training, all sorts of material is something that societies are working with and producing to help move the movement forward. So I cannot find better words to describe what societies are doing than just using what you'll find on the website for the UK, the regional society. So the Society of Research Software Engineer was founded on the belief that a world which relies on software must recognize the people who develop it. Our mission is to establish a research environment recognize the vital role of software in research. We work to increase software skills across everyone in research, to promote collaboration between researchers and software experts, and to support the creation of academic career path of research software engineer. This is what societies are doing, bringing people, advocacy, and training. And so now that we have about 10 years of development of this group, what happened? How successfully have we fought the ancient regime of traditional academic institution? And to answer that question, what we can do is we can look at this society, the first society. We can look at birthplace of research software engineering in UK. And what we see is we see a lot of happy faces. And we see a lot of happy faces that would have not met each other otherwise, most likely. But most importantly, we don't just see the people. What we see is how institutions recognize this. This is a map of institutions in UK that officially recognize research software engineer. So there's a group of people, there's a department, there's a unit, a formal unit recognized by an institution. And this, at the end of the day, is what the RSC movement is about. It's about getting recognition for the critical and vital role the software plays. So this has been going on pretty decently in UK. So now the obvious question is, okay, what about the other side of the pond, the one that we care about? And for that, US is a little lagging behind. So I developed this little script to scrape the internet to find which R1 universities have RSC groups. And as we can see, there's only 12 out of 146 universities that have an RSC group. And actually of the 12, there's a bunch of duplicates because, I don't know, maybe University of, I don't know, Alabama is like 5, and they show up as 5. So yeah, that's less than 10%. It's not great. And there's something else that has happened in US that is very different, that is not what happened in UK. And this is that what we have here is that this problem was recognized, but instead of having institutions tackle it, we have private philanthropy. We have Schmidt Sciences, Sloan, CZI, Simons Foundation. These private funders decided to look at the problem and say, we're going to do something for this, because we believe, many are tech people, we believe that this is something that must be tackled. We have to do something, because if we don't do this, this is it's terrible for academia, it's terrible for science. So we're in the position where private philanthropy is supporting a lot of the efforts to support research software engineering in the United States. And how, okay, now that we have that, now that we have people that are employed to do that, how are we faring? Is it, we're already seeing that 10%, not that great, but what about everything else? Well, we're building community. So one of the ways we're building community is we're also hosting conferences. So the next one is going to be in Philadelphia. It's going to be our third USRIC conference. After you have 2 and you have 3, this is a series now. So I'd say, I'd say that we are following the trajectory that was started by the UK RIC, and we're slowly but steadily building momentum to get more and more recognition and more collaboration and more community, which I think is awesome. And once again, I think community is really a key word, and it's a very important word, not just to support this momentum, to make me feel that what I'm doing is important, and there's other people that care about this, but also because we're actually not alone in this effort. There's more efforts out there that are very much aligned with what we're doing. And here I just want to name a few, because I think these are really important. It's not just the USRIC movement, it's not just research engineer. At the end of the day, what we're trying to do is we're trying to improve science. And we're trying to improve science by tackling software. So here, I want to mention the Journal of Open Source Software, FORT, RMPI, OpenSci, and the Software Commentary. And in the last few minutes of my talk, I'm going to just showcase what all these are doing. And I'll start with my favorite one, and my favorite one is JOSS, the Journal of Open Source Software. And the idea of JOSS is I'm going to use academia to beat academia. Meaning the equation, the paper equals science, I'm going to use that to my advantage. So JOSS is a journal, and it's a completely valid journal. Like a traditional journal that when you go in your reference management system, this works perfectly. It has a ISBN, it has a DOI, all those lot of acronyms. It's a diamond access journal, meaning that everyone can access everything. And it's a journal that runs largely in automation and on GitHub. So the way you submit your paper to journal is, first of all, paper is maybe not the right word, because what you're really submitting is your code. In academia, there's no standard way to cite code. Do you cite the GitHub link, the Zenodo, the paper? So there's no way to track citation for these things. So what JOSS is doing is you can submit your code, and let's stick a small 2 pages paper of it. So other people can cite your paper, but what you really submit is the code. Like the idea is you've proven that you've contributed to science with your code. The scholarly contribution is the code, and then the paper is just this thin shell to allow other people to cite you and you to track the citations. So when you do so, your code gets reviewed. It's not just the paper, the code gets reviewed. And what I love about this is that it happens on GitHub, so you can see it's a GitHub issue, and there is a ton of comments here from the reviewers and the editor, and comments about how to improve the code. And what we're doing here is we're not trying to, this is not an adversarial process. This is a collaborative process. The reviewers are there to help you contribute to the scientific ecosystem. Everyone is aligned because we want to improve, to make sure that your code is good and other people can use it. So I think this is a great way to improve our scientific code with essentially peer reviewing in a healthy manner. And when you go through this review process that everyone can look at, so it's open review, then you get a paper, and a paper that you can look at, everyone can look at, and can be cited. So if you are interested in contributing to scientific projects in open source, a very easy way to start is you go on JOS, you look at the papers that were published. It's like, oh, actually, I'm interested in weather, and there is a package doing weather weird stuff, but I don't care about that, but maybe I can contribute. And I go, and that's good code that you can contribute to, and then people can use. There's a seal of approval to say, this is good code, we like this. And JOS has worked well. In 9 years, I think, the JOS has been around. It has published about 3,000 papers. So 3,000 pieces of code, packages that are now approved. They are good code. This is how we should be doing science. It's reproducible, there's tests, there's documentation, and yada, yada. It works so well that people try to expand the idea from not just open source software for science, but also for education. There's Jose, the Journal of Open Source Education, with the same idea where we're trying to reward people that will spend time to develop educational material, open source educational material, that the traditional academic system doesn't recognize, but we're providing them with a way to get some citation for that, so that using citations, they can advocate for themselves in the academic system. And along the same lines as Jose and JOS and the peer reviewing, we also have Pi in our open side. These are initiatives to once again build community, to once again curate good quality code, provide best practices, and provide ways for the community to help each other identify good code that can be used in science and promote good practices. So Pi OpenSI, you can submit your code, it gets peer reviewed, and then it gets added to this big list of this is good code, I like this. Another example is FORT, the Framework for Open and Reproducible Research Training. This is a large effort to provide tools and do research about reproducibility in the space of science. So trying to see which studies can be replicated, trying to provide tools to teach the importance of reproducibility. So this is a framework for open reproducible research training. It's not a framework for open reproducible research. So there's a ton of material on how to incorporate values of openness, collaboration, and reproducibility within our institutions at the college level, but also even before high school level. And then I'd like to mention one of the earlier players in the space, and this is the Carpentries. So the Carpentries, the software and data Carpentries, they for over almost 30 years have provided a ton of trainings and material to help people, scientists, domain scientists, learn foundational skills in data and software, like how to use Git, why you should use Git or GitHub or things like this. And most importantly, in my view, once again, what the Carpentries did is not just educate a ton of people about the value of reproducibility and openness and testing, but once again is to build a community of thousands of instructors in lots of countries, in different ways, people who believe in the values that we're discussing here, the values of keeping things open, reproducible, and themselves are agent of spread of these key values. So as I move towards the end of my talk, I want to identify what I personally see the values of the movement. And to me, the values of the movement are openness, collaboration, reproducibility, accessibility, is building upon each other's result, is allowing everyone to access science if they want to access it, is reducing barriers, is building things that can be inspected, expanded, and we can use and reuse and so on. And maybe as you look at this, and as you look at this in a Southern California Linux Expo, you maybe recognize that actually these values are not that far from the values of open source initiative. What we're saying at the end of the day is that when we build together, we build better. When we have collaboration as opposed to competition, we can truly advance science and technology. So as I go back and I think about the 2010s, software eating the world, I cannot help but notice that what has happened is that actually the commercial sector realized that this is the way forward. We have, well, Linux, Android, Raspberry Pi, GitHub, Hadoop, a ton of projects, open source projects that were adopted by the commercial sector and that changed our world from big data to personal hardware or, well, Linux in the cloud or mobile phones. There is so much that has changed through the adoption of open source, not because we believe in, or companies believe in specific values, but because they believe that it's just better. So I personally really like this because to me, this is profoundly aligned with what science is. Science is about pursuing the greater good. It's about pursuing the greater good together and with the belief that together we can do better. So as I conclude, I want to just share a very important to me piece of news. The news that today you can join this movement. You can literally find employment doing this, something that was not possible just a few years ago. One of the things that job boards are doing are, the societies are doing, they are curating job boards for roles that are roles in research software engineering, roles that are aligned with these values and roles that contribute towards improving our science. I don't think this was possible just a few years ago. So to me, this is a massive win for this movement, massive win of just a few people that together are trying to change the system. So with all of this, once again, I want to invite you to join our mission. A mission where we push for a research world where code is treated as first-class research output, where software development is recognized and rewarded, and where research code is findable, accessible, interoperable, and reusable. Researchers are equipped with the necessary skills and tools to develop high-quality, sustainable software, and when there's meaningful career paths for those who wish to focus on software. And the way you can join this movement, the easiest way, is just recognize the value of good research software. And with this, I leave my contact information here. As you can see, I'm super excited to chat about this. I believe that this is changing academia for the better. So please join us in this movement, and I'm happy to take any question. Eric, can you maybe...
Oh, can I run it around?
Yes.
Yeah. Okay, there we go.
As I understand, you took the traditional way to graduate from your PhD and then kind of branched off and became a research software engineer. How do you see the path, or do you see an evolution to this training, to this branch that goes from, that trains you to be a researcher? And if I may share, my background is in musicology, and I trained in the field called research creation, so really similar to what you're saying. And in music, a couple of decades ago, they had this problem with musicians being in the academic staff, and what they did was they created specific doctorates called DMAs, or Doctor of Musical Arts. I wonder if you see a similar sort of evolution.
Yeah, this is happening. There is programs in UK, in a couple of universities that are essentially building research software engineering skills. However, I'll say that right now there's kind of an impedance mismatch. What I mean is we need these skills, but there's no one to absorb all these skills. For now, the institutions are not recognizing this, so there's no place, quote unquote, for the research software engineering. So I'd say that we're working on both sides. There's already a movement towards building essentially programs to teach people all these skills, but we need also the other side where we need employment, full-time and permanent for these people.
For things like JAWS, is there a specific list of what programming languages can be accepted into the journal?
So you can use any programming language. There's some requirements. You can use proprietary programming languages as long as you're like Mathematica, MATLAB, as long as your code is open. The requirements are your code has to be for science. Your code has to be not tiny, like at least 1,000 lines, depending on the programming language. Ideally, maybe used for a publication that's not super important. It has to have an open source license, OSI initiative, OSI license, approved license. And then if you use weird programming languages, like if you write your code in your package in Emacs Lisp, you're going to have a very hard time finding reviewers. So you can do that, but maybe it will take like 2 years to get your paper published. So we don't put any, JOS doesn't put any restriction on the programming language.
You had a question? Here you
Well, I was just going to say that depending on one of the reasons, I'm an RSE member also. I think one of the issues is that all the disciplines have unique software. Computational chemistry is different than astrophysics, which is different than music. So we will have to address the issue of uniqueness, and sometimes it's at the level of C, sometimes it's not just at the level of R, Python, and Julia, which are the sort of the low-hanging fruits. I'll just say that one of the reasons for RSE is because of this issue, not despite this issue. It may not be publishing worldwide, but each one of the, as you get deeper into the disciplines, the software gets very funky. But that's the reason we have the disciplines. I'm sorry, I didn't want to interrupt.
No. Yeah.
It's just, this is my life.
Yeah.
Hey, I'm a PhD student, not in the computer science stuff, so I'm very drawn to this talk. But it seems to me a lot of the times in research software, you have people that maybe don't know programming as well, but they know their topic really well, and so they can write their software, and maybe the code's not very good. And on the other end of the stick, there's really good software engineers that don't know the details of the science that you're doing. So is there any things that the organization, SRE, does to bridge that gap?
Yeah, so I think the most common model I've seen is essentially to address this issue by pairing people. Like when you're REC, you don't work, well, depending on the issue, you largely don't work by yourself, you work with a scientist. So you combine two forms of domain knowledge, and domain knowledge in software engineering, and domain knowledge on the subject matter. So I'd say a traditional model is to have a software engineer or a few software engineers embedded in a research project where there's very close collaboration between the two. You also have another side of research software engineering where it's more about the infrastructure. So in the case, scientists are your users at the end of the day. And it always helps to have more domain knowledge on your subject matter. But maybe in some cases not as much. So definitely collaboration is a key word, yeah.
There's seems to be an implicit emphasis here on modeling and data analysis software. Is there a role too for the software that controls accelerometers, that controls telescopes, that controls satellites?
Yeah, great question. I've heard, horror stories about that software as well, meaning you can have your special microscope that has a special way to be run, and the code was written by a grad student 10 years ago, and the code was lost, and no one knows how it works. It just works, but we don't know. So yes, absolutely. And actually, I'd say even more in the sense that when you build software for an instrument, you're building software to support users that do not interact necessarily with the inside of the software as much. So I would say it's even more important in that case that you do this, quote unquote, right. You do this with good software engineering principles. So absolutely.
So we have our RSEs, we have new research software. How do we convince our institutions to kind of get with the times? Because in the lab for biotech, I have used software that's older than I am. And it's a question of what is the cutting edge process and what is the software that matches with that process? Do you have any suggestions for convincing them?
So, okay, I mean, this is what we're here for, in the sense that what we're trying to do is we're trying to convince institutions to buy in our values, because we believe our values produce better research. And we're attacking this problem on so many fronts. One is literally going to head of departments and talking about this and trying to show success stories and, a software engineer spent 30 minutes with a student and made their code 2,000 times faster. This is great, things like this. And then there's the more grassroots side of the movement where we just convince people that there's something out there that is working towards this, and together we can have enough pull on the system to change the system. So I don't have a good answer, and we're all looking for the best answer because we all want to be in this future where everything is good. We want to get there as fast as possible. I think I'm hopeful because the UK has shown success stories, big success stories, like where institutions have recognized this, and now you're almost, I wouldn't say required, but when you write your funding proposal, you're recommended to have a section where you say, actually, I'm also going to hire a 0.5 FT research software engineer because I know that this is what leads to survival to the project. So as we move more and more towards that, I think there's more, it's going to be weird not to have some of that. So peer pressure is going to help us get there. And when I think about US in particular, and thinking about institutions like Princeton is very much leading the way in all of this. When you're a Caltech and you see, oh, Princeton is doing that, then Caltech also wants to do that. So there's things like this where there's a little bit of moving together, and then we'll become more and more normal. Yeah, it's not a good answer, but yeah.
Hi, I think. I figured that I imagine that as not only as you sort of convince institutions, you convince faculty, like people who are currently in charge, sort of it's like a horizontal sort of persuasion. I imagine there's also sort of as new people who are aware of this, younger people who become into these more senior positions. I imagine that also help further this movement. But I'm an undergrad in CS, and I think a lot of my peers have this sort of very short-sighted notion that CS research, or research as a CS person, is just, I'm going to go work in the AA lab. I'm going to work in the computer vision lab.
Mm-hmm.
And I think a lot of them don't realize that their skills are so heavily applicable elsewhere.
Mm-hmm.
And in fact, I work in biology a lot. My earlier PI was telling me, like, right after I left the lab, he was like, how do I find more CS people? How am I going to replace you, man?
Mm-hmm.
And so I want to know, do you have any thoughts, do you have any recommendations on how you can sort of convince the CS side that they should go into research?
Yeah, so the first step is you should give a talk about this to your peers. So this is how we do it. I hope that someone here in the room didn't know about what I talked about today, but now is aware of something new and can themselves align to the movement, or just know that there's something out there and they can point people to this. So I believe that this is very powerful. It's just show that there's alternatives. Other than that, if you want, many domains have interesting problems that are not domain-specific problems. Like in the case of biology, it could be how do you analyze 1 petabyte of data efficiently, what data structure you have to build, and things like this. So yeah, traditional research in CS is indeed kind of standard, but there is a lot of applied CS research. So maybe bringing up those problems can be, and sharing your experience can be a good way to show that there's an alternative.
One more question.
Yeah.
So I work on this, and in a big research group at USC. And I want to tell you an anecdote first, and it's something like I recommend, something that that people talked about here that I think we are kind of helping. The anecdote is the following. Right when you said 2014, 2015, we were going to hire in a tenure track the guy who wrote R. Mm-hmm. And he did not get hired. So that tells you that even at that time, my boss was is a pioneer in this field, and he recognized the contributions of somebody like Gentleman. That's his name, Robert Gentleman, who wrote R. But still, I think he's not tenure track yet. So after that, we had run into the same problems that were faced here. People that know how to write code, they don't know anything about science, and vice versa. So we created a degree. You have to create a degree, computational something, computational physics, computational chemistry. So you get a degree in computational something. Like we created computational biology. Actually, it's quantitative and computational biology. So people that graduate in this field will have both skills. Without that, you're gonna graduate biologists who still don't know about data structures or algorithms, let alone algorithms. Nobody passes algorithm anyways. So, so it's that's the way I see it. So the schools have to come up with these courses and careers, because you mentioned it you said very well. These careers do not exist. And anyway, it was just a comment.
Yeah, I think we need both sides. We need people pushing for this, and then we need institutional support. Yes, so we'll get both, and we are working for both. So I think, unless there's any more burning question. Okay, thank you all for this, and Hello, everyone. Welcome to Developers, Day 3 of SCaLE. It's my pleasure to introduce Emily, who's going to tell us about the future is real-time data. Let's welcome Emily.
So hi, everyone. Thank you for joining me today on this presentation about real-time data. We're going to be talking about this technology called stream processing, which is a specific way that we process data. I'm Emily. I was previously a technical writer and developer advocate at Rising Wave Labs, where they were building Rising Wave, a stream processing database, and we'll get into exactly what that is a bit later. And there I was working on documentation and just building runnable demos to showcase how Rising Wave and stream processing can be used in different industries. So today we're going to be exploring stream processing, a powerful method of data processing that allows us to work with information as soon as it's generated. As our world becomes more data-driven, organizations, companies are generating massive amounts of data or getting massive amounts of data every single second. So think of like your finance industries, your e-commerce industries. So the ability to process and analyze this data instantly is crucial for making fast and informed decisions. So today we'll be breaking down exactly what stream processing is, comparing it to our traditional method of data processing known as batch processing, and then going into talking about where stream processing is used exactly in real-world applications. And then we'll be moving on to how to build a data pipeline that's suitable for stream processing, like the different types of data platforms that you'll need. And then at the end, I'll go through a live demo of what that data pipeline would look like and how stream processing looks like in action. So to start, what exactly is stream processing? Stream processing is a method of handling data where we continuously ingest, process, and analyze information as it arrives. So instead of waiting for data to collect over a specific period of time, stored, and then analyzing it, stream processing enables real-time insights and immediate responses. So the traditional method is great for large-scale analytics, but it introduces latency, so your decisions are made based on older data. This works in certain cases and is probably applicable in most of our general use cases, but in stream processing, this is perfectly suitable for cases where you need to process real-time data. And a key concept in stream processing is the data stream. So instead of working with files or buckets of data, we're working with data streams, which are continuous flows of records representing individual events. Some examples can be like clickstream data, where you're tracking user interactions on a website or app in real time. Financial transactions, where you're monitoring payments looking for fraudulent activity. IoT sensor data, where you're analyzing environmental conditions, equipment performance, or smart home devices, or login telemetry data, so you're observing system health and security threats in real time. So now that we've established what stream processing is, let's compare it to batch processing. So if you're already familiar with just general data processing and data pipelines, the concept of batch processing might come to mind. Usually if you're doing any sort of reporting, creating ETL pipelines, or creating machine learning workflows, you're probably using batch processing. So let's compare it so you get a better idea of where stream processing stands. So batch processing is a method of data processing where we're collecting data over a specific period of time and then processing it all at once. This is usually done on a scheduled basis. So this could be hourly, daily, weekly, monthly. And since batch processing handles data in bulk, it's very efficient on large data sets, and it doesn't require continuous monitoring since, unlike stream processing, data isn't coming in consistently. However, it does introduce the concept of latency because you only get the results after an entire batch of data comes in and is processed. So if we think back to stream processing, data is continuous and it comes in real time. Batch processing comes in chunks. And then in batch processing, higher latency, stream processing, lower latency. And lastly, batch processing is generally more resource efficient because you can choose when to process that data. So you can pick a particular time where your device, or where more resources opened up so you can use it to process this huge amounts of data. But in stream processing, you don't really get to choose when to stop the pipeline if your data is coming in constantly. So to make this idea more concrete, let's think of a particular example where stream processing is better and when batch processing may be better. So if we think about the finance industry or the banking industry, and we want to monitor for fraudulent activity, when it comes to batch processing, it may not be that efficient or that useful if we're only able to find fraudulent activity after like an hour or a day. You ideally want that notice to come in instantly. So in that case, stream processing would be perfect because you can process your data down to the second or millisecond and inform your customers whenever something fishy comes up. But if you're looking at your monthly budget or your quarterly report, then there's really not a point to use stream processing to keep up with what your budget looks like every single second. You can do it on like a daily basis or a weekly basis based on whatever you need. So while batch and stream processing seem like completely two different approaches, they actually exist on a spectrum where somewhere in the middle we have micro batch processing. So earlier I said that batch processing, usually the data comes in like hourly or daily. You might have the idea, well, what if we just break down those batches into like really, really small batches, like minutes or seconds? And that's exactly what micro batch processing is. It's an approach that aims to minimize latency while still maintaining some of the efficiencies of batch processing. And since these batches are broken down into really, really small time segments, this makes it almost near real time. But usually these batches aren't going to be any smaller than a second. If you can get your batches down to a second, that's already going to be very efficient. And most frameworks that do support micro batch processing, you probably can't get it down to a second, especially if you're getting in a lot of data. So stream processing, on the other hand, you can get it down to sub-second to like milliseconds. So none of them are like the correct way to process your data. It really depends on exactly what you're trying to achieve. So if you need high throughput, like if you have a lot of data and you don't really need real-time insights, batch processing is perfect. If you want low latency but some delays are okay, then micro batch processing is perfectly fine. And if you just need whatever is the fastest possible, like I need this result right now based off of whatever's the freshest data, then you would want to choose stream processing. All right, so now that we have a solid understanding of how stream processing works, let's talk about exactly where people are using stream processing. So I've broken this down into 4 categories. Streaming analytics, where we're extracting real-time insights from fast-moving data. Event-driven applications, so systems that can react immediately to events as they occur. Real-time data enrichment, where we're adding additional context to our data streams, and feature engineering for machine learning models. All right. So let's start with streaming analytics. So this is usually when you have high velocity data streams and you want to continuously process and analyze that data for instant insights. And this is probably most applicable in the stock trading and algorithmic trading. So financial markets are generating an enormous amount of data every single second. I'm sure a lot of us look at the NASDAQ stock tickers throughout the day, and it's changing every single second. So stream processing enables us to process that data in real time. We can look at the market trends, the order books, and the price movements as they happen, and we can process that data, analyze that data, and it enables traders to make split-second buys or sell decisions. And then another good example would be sports betting or like live event tracking. If you're looking at any type of live sports, things are changing and happening very rapidly. So you want a data processing system that can process those data points and allow you to understand what's happening. Or if you're doing like any sorts of sports betting stuff, those betting odds would be adjusted dynamically to allow your users or your audience to get the latest insights. And another example would be IoT monitoring, so sensors in industrial equipment. If you work in any sort of lab, you probably have those like temperature trackers just to make sure that whatever environment you're in is at the optimal temperature and humidity. And cybersecurity, again, you're just monitoring network traffic, and you want to do that constantly, and you want whatever's the freshest data so that if anything happens, you'll be notified instantly. Then the next use case that I had up was event-driven applications. So event-driven applications is when you're reacting to the events as they happen. So rather than just looking at whatever statistics is popping up, you're actually doing something or the program that you're building is reacting in response to that. So many modern applications, particularly in microservice architectures, are built around event-driven processing, where different components listen for and respond to real-time data. So some examples could include like fraud detection in banking. Banks can analyze transactions as they occur and flag suspicious activity based on real-time user behavior. So if they know that you're in one state, but for some reason a transaction from a completely different state or country pops up, they can notify you instantly. Another example would be like customer engagement. If you pull up your Netflix account, your recommendation is going to be constantly changing based off of your previous views or just whatever user profile they've built up around you. And then system monitoring, so IT teams can monitor logs and performance metrics in real time, and if a web server starts experiencing an unusual amount of traffic, they can automatically trigger something to help the system before everything crashes. And next, we have real-time data enrichment, and this is mostly just combining your incoming data streams with external or historical context to enhance decision-making. And this sort of goes into the concept of a hybrid batch and stream model where you're able to process both streaming data and batch data on the same platform. So this could be very useful in like ad tech and like advertising, when an ad platform bids on an impression in real time, it can enrich raw bid requests with historic user data, browsing behavior, to determine the best ad to serve. E-commerce, so any online store can dynamically adjust prices based off of like real-time demand or user behavior so that they can maximize their profits. Or supply chain and logistics. So in this case, shipping companies can use real-time data to optimize their delivery routes based off of existing traffic conditions and weather forecasts and fuel costs, so that their operations are running at peak efficiency rather than just going through the same routes every single day or trying to optimize those routes after something has happened. And the last use case is going to be feature engineering for machine learning. So this is a more advanced application of stream processing, since you do have to combine it with a machine learning model. So in machine learning, features are the inputs that models use to make predictions. So for real-time applications, these features can be generated instantly as new data arrives, instead of being built previously on old data and then just using the same few features over and over again on new data. So some good examples would include like AI-powered customer support bots. I think they're becoming a lot more popular now on a lot of sites, where you go on the website and instantly a text box pops up and you're chatting with a chatbot instead of an actual person. But we can improve these chatbots by employing stream processing, by having the chatbot react to real-time user interactions, use sentiment analysis and historic customer data to adapt their responses. And since we're using stream processing, they can continuously learn from new interactions, ensuring that feature vectors and the machine learning model is always up to date based off of our newest data and how our current customers behave. Another good example would be real-time risk assessment. Specifically, if we think about like the healthcare industry, this would allow for better patient care, enabling faster response times, better predictions, and improved patient outcomes. Healthcare providers can extract features from real-time data sources, such as any type of wearable devices, ICU monitors, and electronic health records to prevent critical medical conditions before they escalate. So instead of using like historic data and gathering all of that data in one place, they can update their analysis consistently to ensure the fastest possible decision-making process. And then the last example I have for today, in this case, is going to be predictive maintenance. So sensors on industrial machines can continuously generate telemetry data that which can include vibration patterns, temperature fluctuations, and like efficiency metrics. And you can transform these data points into real-time features that help you predict equipment failures before they happen. And this will make the entire operation more efficient, so that you don't have to schedule maintenance based off of fixed intervals. Instead, you can be more proactive and prevent failures from happening before they actually do. So now that we know where stream processing can be used, let's talk about when you shouldn't use it, because it's not the only choice out there. So some use cases where you don't want to use stream processing would be any type of large-scale historical analysis. So if you're running like annual business reports on like a huge amount of historic data, there's not really a point to use stream processing, because you can just use a batch processing platform that's going to be much more efficient and save on compute resources. Another one would be ETL workflows for data warehousing. So a lot of organizations just use batch pipelines to manage that data for offline analytics, and it works perfectly fine. There's not really a reason to like change over to a new method. And the last one that I have is going to be regulatory reporting and compliance. So some industries have strict compliance requirements, and you're not going to need real-time processing for that. So in any of these cases, it's really going to be dependent on exactly what your requirements are in regards to latency and what resources you have available in terms of actual compute resources, as well as like actual human labor. All right. So now we can move on to how to actually build a data pipeline that enables us to do real-time data processing. So unlike traditional pipelines, a stream processing pipeline needs to handle continuous unbounded data streams, and unbounded data streams are just streams of data where there's a specific beginning, but there's not a specific end. So it can keep on coming in forever, and you'll need a way to deal with that. So to handle this efficiently, we will need several key components. A pub subsystem to ingest and distribute streaming data, an actual stream processing platform where we can transform, enrich, and analyze the data, and a storage layer to process data for like future use. So let's start by breaking down each of these components, starting with the pub subsystem. So a publish subscribe system is a messaging infrastructure that allows data producers or publishers to send messages to a central broker from which data consumers or subscribers can receive them in real time. So instead of directly connecting producers and consumers, pub subsystems act as an intermediary layer, ensuring that data flows smoothly and efficiently between them. So why do we need this like in-between layer? Because wouldn't it be easier to just skip that part and just send it directly to our processing framework? So decoupling our producer and consumers is actually a good thing, because instead of sending data directly to an analytics system, this creates this dependency between your producer and consumer. So if your analytics system is down or slow, the producer either has to wait, or if it's down, then you just lose all of that data in between that time. So a pub subsystem removes this bottleneck by allowing producers to send data asynchronously while consumers pick it up at their own pace. And that just makes everything a bit easier. And it allows you to handle high velocity and high volume data. So many applications can be generating thousands up to millions of events per second, and it can be difficult for your analytics platform to directly consume all of that efficiently and process all of that. So this pub subsystem acts as a buffer, ensuring that no data is lost while it's being processed. And it also enables multiple consumers. So a lot of the times companies have like multiple use cases using the same data stream. And so having this pub subsystem allows different teams to ingest specific parts of that data, and they can use it for whatever they need. So an example could be like a stream of e-commerce transactions can be used for both fraud detection, recommendation systems, and operational monitoring. And for each of those cases, you're probably not dealing with like the exact same data set each time. So having that pub subsystem makes it a bit easier to just choose which streams of data or which sections of data you want, and then process it more efficiently using your processing platform. And lastly, the pub subsystem allows for fault tolerance and scalability. So if one consumer fails or slows down, the pub subsystem is able to store the messages until it's back online. And most modern systems are distributed, so you can scale them across clusters for further fault tolerance and also for scalability. So let's talk about two of the more popular open source frameworks. The first one being Apache Kafka. So if you've ever worked with streaming data or not, you might have heard of Kafka. It was originally developed at LinkedIn, and it's designed to handle high throughput real-time data streams reliably and at scale. Right now it's sort of like the de facto standard for distributed messaging, and it's used across a lot of popular industries and at very well-known companies. So at its core, Kafka is a distributed event streaming platform that enables applications to publish, store, and consume messages in real time. Unlike traditional message queues, Kafka is fault tolerant, scalable, and designed for high availability. So Kafka allows your messages to be persisted allows your messages to be persisted because it's built on a distributed log-based architecture. So the messages are written to append only logs, and stored across multiple brokers. So this allows Kafka to retain messages for a configurable period, so that could be minutes, hours, or days, and this allows consumers to replay past messages without affecting their performance. So if a system goes down, they can pick up where they left off. Secondly, Kafka scales efficiently using partitions. So whenever you get a message is stored within a specific topic, and then that topic is split up into multiple partitions, which are then spread across brokers. This enables for parallel processing, making Kafka ideal for handling high throughput data streams like financial transactions or order processing. So just to sort of just to sort of like summarize things, so the key features of Kafka include like its high throughput, scalability, persistent storage, and strong ordering guarantees. So messages within a partition are strictly ordered, but because topics have multiple partitions, ordering between partitions are not guaranteed. It's only within the partitions. And a rich ecosystem. You can easily connect Kafka to a lot of different other frameworks. And for the sake of time, I am going to skip over Pulsar. Pulsar is just another option, and it's very similar to Kafka, but it has a two-layer architecture, a broker and a bookkeeper. So brokers just handle real-time messaging. So they take the message from whatever publisher you have and then send it off to a consumer. And then the bookkeeper is in charge of storage. So that means you can scale them independently of each other. You can scale the storage layer without increasing the number of brokers you have. And one point to mention is geo-replication. So the architecture natively supports cross-region replication, allowing data to be mirrored across multiple data centers without complex configuration. On the other hand, for Kafka, if you want to do that, you're going to add in additional components independently. And one of the last key feature to mention is the message TTL policies. So Pulsar will automatically clean up old messages to optimize storage. So that makes it a bit easier on you, and you can save on your storage resources. And at the end of the day, whatever you want to choose, it's going to be dependent on your use case. If you just know you're going to have a lot of data, then Kafka is probably going to be a better fit. And Pulsar is ideal for like multi-tenancy, geo-replication, and dynamic cloud scaling. Right. And then the actual processing part of the pipeline is the stream processing platform, which is a specialized system that allows you to analyze, aggregate, and filter event streams as they arrive. Unlike traditional batch processing tools, this stream processing platform is going to operate continuously without stop. And since it operates in memory, it allows for low latency processing, so just doing things really quickly, event time handling. A lot of times your data streams are going to have a timestamp associated with them, and for many use cases, ensuring accurate analysis based off of when the event occurred is very crucial. And lastly, stateful computations, so that just means you're able to keep track of ongoing trends in the data system. Right? And then I'm going to briefly cover two stream processing platforms, first being, this is just what the stream processing platform, its position in the data pipeline. So it's ingesting data from various data sources or brokers or databases, doing the analytics within that platform, and then you can offload it to a storage platform that you're using or a data visualization platform. So to start, I'll briefly cover Apache Flink. So one of Flink's biggest strengths is its ability to perform stateful computations efficiently. Flink can maintain state across events, making it ideal for applications that need to track changes over time. And in order to ensure proper time ordering events, Flink uses watermarks, which act as timestamps that track event progress. And this allows Flink to wait for late events within a specified time window, order events properly, and prevent incomplete results. So, and one key feature to mention is exactly once semantics. And this just ensures that every single event that comes into the system is processed exactly once, and this is mostly done for the sake of accuracy. And it is, I think, one of the more well-established stream processing platforms, so there's a very well-established ecosystem and community, so if you ever have a question, it's probably answered on Stack Overflow already. And next, I'll be talking about Rising Wave. Rising Wave is a stream processing database. So on top of the processing part, there's also a storage layer so that you can persist your storage results afterwards. It is the storage and computing nodes are decoupled, so you can scale one without the other based off of your current use case. It is Postgres compatible, so if you want to hook Rising Wave up to any other platform, you can do so using the Postgres wire protocol, making it really easy to integrate it into any sort of data pipeline that already uses Postgres. It's available as both open source or cloud. Open source, that just means you can download it, run it as is, and cloud if you want a managed version, so you don't have to deal with any of the setup. And it handles both batch and stream processing, so you can run ad hoc queries as you need on batch data. And one thing to point out is that it is SQL native, so all you need to learn in order to run Rising Wave is how to write SQL queries, which makes it really easy for most people who are already familiar with data processing, since SQL is probably one of the more popular languages taught. All right. So just a little bit more detail about what Rising Wave is. It's a distributed SQL stream processing database, and it's purpose-built for processing streaming data. And the community is ever growing. And again, I've touched on quite a bit of this already, some of the advantages of stream processing using PostgreSQL, since again, Postgres is such a popular relational database. It's really easy to just get started with Rising Wave, since a lot of it is going to be exactly the same. Right. And again, if you're choosing the right one for you is going to be dependent on what you need to do. Flink's advantage is that it does allow for a little bit more advanced transformations. On the other hand, for Rising Wave, you're a bit more limited since you're mainly using SQL. You can create some user-defined functions, and that allows you to do a little bit more advanced transformations, and you can include external libraries from Python and Java if needed. And the last part of the pipeline is going to be your storage or a dashboarding layer, and this is going to be optional based off of what you're doing. So since Rising Wave also has a storage layer, you don't really need external storage if you don't want to. But if you do need it for whatever other applications you're building, Rising Wave does have a very diverse set of connectors that allows you to offload your data to different platforms, whether it be some sort of time series database, Apache Iceberg, Amazon S3. And dashboarding is probably going to be a lot more popular. Most stream processing platforms don't have a built-in visualization part. So if you do want to create dashboards to easily monitor your system, you can attach them to a dashboarding platform such as Grafana or Apache Superset to build your dashboards. All right. And now that we talked about how to build a pipeline, I'll go through a live demo of what that pipeline can look like. So for the context of this demo, we're going to be sort of simulating a energy company, so sort of like PG&E, and how they would monitor a community of homes and each home's energy usage. And so our data pipeline is going to include a data generator for the sake of this simulation, and that's just going to simulate how much energy each household is using every single minute. And then we'll have Kafka as our broker, and then we'll also be using Postgres as additional storage for some of the customer data, so what type of plan they're on, what address they're at, stuff like that. And then we'll be using Rising Wave as our stream processing layer to transform that data to get meaningful insights on how much energy each house is using, and predicting their monthly bill at the end of each period. And at the end of this pipeline, I'll have a dashboard set up that allows us to easily monitor all of these things. All right, and I'm just going to switch over the display. Okay. Right, so this demo is available at the Rising Wave GitHub repository under the awesome stream processing repo, and you can find it under solution demos, energy grid, and you can pull this bit of code to your device and run it as is using Docker. I think the only thing that you'll need to install is PostgreSQL. Any version that is earlier than 16 is going to work perfectly fine for this. So we can go ahead and start it up. I was testing it earlier today, and this will start all of the necessary components. And for this demo, I have Zookeeper and Kafka as our pub subsystem. Kafka uses Zookeeper to run. And then the Kafka producer is our data generator that's sort of simulating 20 households' energy usage throughout time. And then our Rising Wave instance to process data, and then the Grafana dashboard. I also have the Postgres database set up, as well as this is just the script to create a table in Postgres and ingest it or inject some data into it. All right, and then to start Rising Wave, since this Rising Wave instance is already started, I can open up a terminal shell here. And these are just the default parameters you use to get access to the Rising Wave database. Right. And once we have Rising Wave started, all we need to do is, I already have the code ready here in the GitHub repository, so it's a lot easier to test out this demo. So we'll start by connecting to our sources. So in order to connect to any sort of data stream, so from like Kafka or Pulsar, we can use the create source command here. And here we just define the schema of the data, so what columns you have and what data type they are, and the connector parameters, so what type of connector are you using, what topic you're consuming from, the Bootstrap server, and you can further customize this by specifying from exactly which time point you want to start consuming data from, and like security authentication options are also available, but for a demo, that's not really necessary, and we can just copy those over. So when you create a source, you can't really query from it just yet because it just creates that connection. It's only after we create a view on top of it, or a materialized view in this case, where it actually starts ingesting data. However, if you do want to also store this data within Rising Wave, instead of using create source, you can use create table, and everything else is the same. So a table persists the data in Rising Wave, a source just creates that connection. And then in order to connect to our Postgres database, it's going to come in two parts. So first, it's going to be a create source command that won't copy over. So that creates a connection to the Postgres database. So that will include like any sort of login credentials you used for this database, the port you're on, the username, the password, the database, and then because a lot of people have multiple tables that they want to ingest data from, you can then create tables based off of this source, making it a lot easier if you want to ingest data from multiple tables. So the source creates the connection, the create table actually ingests data from the Postgres database. And this is a CDC connector, which means that if you make any changes to your source Postgres table, those changes will also automatically be reflected within Rising Wave. And in this case, you can query from the table. So if we just count the number of customers, we'll see that we have like 20 households set up. So once we have our sources, we can start creating materialized views. So a materialized view stores the results of a query, but the difference is that it's going to be constantly updated as new data comes in. So it's always going to give you the freshest results based off of the freshest data. And one extra feature that I added here is a user-defined function that counts the number of days that are within each month. So some months have, I think in Postgres there is a built-in function for this, but it doesn't exist yet in Rising Wave, so I had to define the logic separately, which is not copying over. And then we can start creating materialized views to track different aspects of energy consumption. So in the first case, this just tracks the amount of energy each household is consuming within 5-minute intervals. In this case, I have both a energy. So it actually stores the results of your query, and it gets updated every time new data comes in. So it's always going to be like the same set of data, it just gets updated. Yes, these are updated automatically. Yes. Yes. So in this particular demo, I have the households both consuming and producing data. So producing in the sense like, oh, they have solar panels. So this calculates the net consumption, which is going to be the amount of energy that they consumed minus the energy that they produced. And then we can just query from it, just to see what that looks like. So since it is midnight, there is no energy produced. Since I'm assuming they're using solar panels, there is no sun. And then the next query is going to be keeping track of how much energy they've used throughout this month. And this notice just is about the time zone that I'm setting. I'm not using a time zone, so it's just automatically going to be set to UTC. The next two queries separates the customers based off of what payment plan they're on. So if they're on a tiered system, it just calculates their monthly bill based off of the total amount of energy they've consumed. If they go above a certain amount, they're going to be charged more for each unit. And then the other one is going to be time of use. So the amount they're charged per unit of energy is going to fluctuate based off of what time of day it is. So during peak hours, they're going to be charged more. And then the next few queries are going to be calculating the bills for each customer based off of what payment plan they're on. So the first one is going to be calculating their current bill for tiered customers. And then the next one is going to be estimating the bill at the end of the month for the tiered customers. And this is just going to be a really simple estimation based off of average usage so far over the month. And then we're going to be doing the same thing for the customers who are on a time of use plan. The same pay bill so far, and then estimated bill at the end of the month. Right? And then once we have all of those queries set up, we can then open up this Grafana dashboard that I've already set up with all of these visualization panels to keep things easier for everyone. So these are just basic summaries of the current monthly usage throughout the entire community and the estimated monthly usage at the end of the month. And here we're just keeping track of the simulated time within the data generator. So right now it's on May 2nd, 1997. And again, just keeping the net consumption throughout the entire community for this hour, for this day, and then for this month. And the consumption is going to fluctuate throughout the day. If there's nobody at home and in the middle of the day, there's less energy used. Also, there's less energy during this time because the sun is actually out, so the solar panels are collecting energy, so the net consumption is going to be much lower. At night, people are home, there is no energy produced, so the net consumption's a bit higher. And then same thing here, net energy consumption throughout all of the 20 households throughout the day. It's higher at night, and then higher at night, lower in the middle of the day. And since we're still going through like this period of time, this data point isn't fully updated. Same thing here, just average energy consumption. And then at the bottom, we can compare the bills between the two different payment plans, where the tiered customers, we see that their current bill is lower, but their estimated monthly bill is going to be higher at the end of the month compared to the customers who are on a time of use payment plan. Their estimated monthly bill is going to be lower. And since I am using a data generator, there's not too much variance between how much energy each household consumes. So the total energy used so far and estimated total energy use is going to be pretty much the same. So yeah, if you do want to test out this demo, again, it's available at the Rising Wave GitHub, Rising Wave Labs GitHub, awesome stream processing repo under solution demos and the energy grid. Just minor caveat, when I initially set this up, I didn't specify a version for Postgres. I think right now if you automatically pull it using Docker, it pulls version 17, which isn't compatible. So you will need to change that here, just anything under 16. I chose version 12 and everything will work just fine. And yeah, that's it for this presentation. Thank you all for coming.
Questions?
Thank you for the presentation. What is the flow of messages in this demo? So the publisher publishes the message to Kafka, and then does Rising Wave store the message for some period of time?
So in this case, Rising Wave does not store the raw message because I used a create source statement. If you do want Rising Wave to store it, you can use create table. But once you actually process the data and start creating materialized views, all of these results are stored within Rising Wave.
And updated on every new message?
Sorry?
And the view is updated?
Yes.
More questions? I don't see any more questions, so let's take the opportunity to thank the speaker again. Oh, yeah, right.
Yeah.
So, there's a switch here. Okay. So you can turn this on.
Perfect.
You can get friendly, so you can just turn it off. Yeah. Okay, you can turn on there. There's room here if you, there's a few seats. Hello, everyone. It's a pleasure to see a room full because it makes me feel good that I'm not the only one that needs some unpacking Git. So it's an honor, and I'm very excited to introduce Tanya and Nick. Was Nick right? Sorry, sorry. And they're going to tell us about Git. So please take it away.
Thank you. Thanks a lot. Super hyped to be here. Also, excited how many people actually want to learn about Git internals at this time of day on a Saturday. Wow. Woo! Give yourselves a round of applause, please. Woo. Okay. Cool. So, we're going to talk about Git. And first, I would like to start with a survey. Who here actually have never heard of Git? Good. What I expected. Awesome. Who actually uses Git in their day-to-day life? All right. Almost everybody. I would say everybody. Who doesn't use Git? Okay. Okay. So, yes. Thank you, Ben. All right. So Git, as known, is a version control system. It is distributed and collaborative. It's been around since 2005. It was developed by Linus Torvalds as actual versioning system. And I would say Git is inseparable from open source, and it's been gaining its popularity since GitHub launched in 2008. And actually, nowadays, I would claim that it's an industry standard because there are some people who cannot actually imagine the world without Git because they've never worked with anything else. For instance, myself. So who actually worked with other versioning systems? Because, some of you are mature. All right. No, it's fine. Right. But first, let us introduce ourselves. Nick, take it away.
I'm Nick Lewis. I'm from Portland, Oregon. We're both, I'm not sure if we say it here explicitly, at Phlox. You can come find our booth in the expo hall. Probably not later. I think we're done after this. But tomorrow, we'll be there all day. Yeah, I'm an engineer. Phlox.
Awesome. So, yeah. And a great puppy dad, I would say. Yeah. So as for myself, I'm also a software engineer. I work at Phlox. I'm based in Karlsruhe, Germany, and I do a bunch of things. Maybe too many things. But currently, I mean, it's a gardening season. Got to start your seedlings and stuff. So this is my current main project. But let's continue. So, as Nick already mentioned, both of us work at Phlox, and I would just like to do another survey. Who of you has already heard of Phlox? All right. So I think we've done a pretty decent job this conference. So for those of you who haven't heard of Phlox, it's kind of important for our talk. So I'm going to mention it real quick. Phlox is an open source tool. It consists of the CLI, which is free and on GitHub. And Phlox allows you to create environments, install packages into those environments, and activate them. It's very handy. You can try it out. Again, stop at our booth or just download it. So this is the CLI, but Phlox actually has the second component, which is Phlox Hub. And Phlox Hub is the part of Phlox that Nick and myself work on. This is our web platform where you can browse through all the packages that you can install with Flux. You can also share your environments with your friends and look at other people's environments. So while working on Flux Hub, we actually got pretty deep involved with Git and had to learn a lot about Git internals. And this is what brings us to this talk today. To Unpacking Git, actually almost a self-help guide that I wish existed a year ago while I was starting, Nick, you had more experience with the Git, I'm just talking about myself here, learning about Git, and an unofficial title is Understanding Git Internals Fast. So I hope after this talk, all of you will have some idea of how Git works internally and how it's built. All right, so we're gonna start with a question. How does Git work? This is the question we started with. And the answer, the picture that we had, or some of you might have, is pretty straightforward. Git consists of repos. It's a set of branches. A branch consists of commits. It's a set of commits. And a commit is a kind of change that I introduce. So it's a diff, right? And oftentimes if you read or browse on the internet about Git, you can visualize it as something like this. It's like we have two branches, they have commits, and those commits have some sort of IDs, and this is how Git works, right? Well, spoiler alert, not really. Not really. And today we want to debunk some of these, I wouldn't say misconceptions, but basically, how else would you know? And actually tell you, how it really works. And to start with that, we need to talk about objects. Oh, also, a very important disclaimer. So this talk does not claim completeness in any sort of form. If you want a complete overview of what Git does and how it works, please refer to its repository in the source code. We can only share our knowledge and our understanding of things. Yeah. So when we start talking about Git internals, we need to talk about objects, because Git has a defined object model. Git consists of 4 base objects. They have something in common, and that is that they are addressed by a unique hash that is created based on their content. Sounds kind of theoretical, but we'll show you how it works. Those objects are also linked between each other, and they're stored in an object database. And so sometimes some of you might have heard that Git is actually a file system, a database. This is maybe why. And so those 4 base objects are tag, commit, tree, and a blob. And we're going to start with the most important concept, which is hashing. I mentioned that objects are addressed by their hash. And to do so, Git uses the SHA-1 algorithm out of the box. It calculates a 4-character hash based on the content of the object it is currently looking at. And this looks something like this. This is what we recognize, right? This is what you see all the time when looking at GitHub or just using a Git tool of any sort of kind. And this is a very important concept, as you will see, because it's at the core of Git. Oh. Right, we're going to start with the first object that is very common, that all of you use every day, which is a commit. Commit is something that we use to complete our changes, to complete a set of work. We annotate the set of work with a message. Might be a meaningful one, might be a less meaningful one. But basically, internally, commit is represented with its hash. It includes special metadata about the author, creation timestamp, and a message. And what commit actually represents, and this is very important, it's not a diff. Commit actually represents a snapshot, and not only of those files that you have changed, but it's actually a snapshot of the entire repository at this given point of its history. And this is one of those misconceptions that we felt was important to debunk. All right, let's get started with our first demo.
All right, I don't know which side my terminal is on in spaces, so we have a 50% chance of finding it. There it is.
Woo.
All right, I'm going to keep making it bigger until someone says stop. Is that okay in the back? It's good? All right. It's enormous. Okay, so I am going to go back to my empty repo and have I Git initted? Yes, I'm going to start an empty Git repository. And I'm going to start by putting some content in it. There's a lot that's going on here, so we're looking at an object graph, as we'll talk about in a bit, and we have to look at one of the parts of that graph. So there's going to be some things that we don't quite touch on yet that we'll get to, and we'll just hand wave some things. So, hello, SCaLE. I'm going to make a file, test.txt, and I will add that, and I will commit. Hello, SCaLE. Now this is the first commit in my repo, so it is a what's called a root commit. It doesn't have a parent, and git commit prints this helpfully here, root commit, to let us know. But then it says this is actually a very fun hash, but that is the commit hash, and the common commands you'll use for this are git show, which shows the commit, the author info, the date, the commit message, and then a diff. You can also see git log of my branch, and I can see I have one commit. It has no parent. But there's also a command, git cat file, that we're going to rely on a lot today, which is a way of sort of pretty printing the Git representation of this object rather than the sort of user-friendly interpretation of it. So we'll git cat file. First, we can do a -- type, I will say. Nope, that's not what that stands for. Does it support, maybe? Oh, it's just -t. Here, I thought I was going to be friendly. -t. And that just tells us that object is a commit. And I can do -p for pretty print. And this is the info as Git understands this object. It has a tree identified by hash. Again, we'll get into that in a moment. But as Tanya said, the commit represents the entire content of the repo. That is the working tree. It has an author, which is me, and a timestamp, and a committer, which is also me, and a timestamp. That's important if you're using these days on GitHub, GitHub will rewrite the commit info sometimes when you merge or rebase. But if you're using a patch workflow where you mail patches to a mailing list and then someone downloads them and applies them, there you want to track who actually wrote that patch and then who put it in the code repository. So that's why author and committer are two separate fields. And then my commit message. And I'm going to make a second commit. You'll see that this one doesn't have a parent listed here because it's a root commit. So I've been trying to figure this out all week to put it in the presentation. Is this A supposed to be capitalized or not? I've seen it both ways on the website. So I'm just going to change it. And I will commit that. We had a section in here about good commit messages, which is kind of tangential. We removed it for time, but don't do this. You can see the new commit SHA, and if I cat file that commit, you can see it has a new tree. Well, you can't see that because you can't see the old tree. Here's the old tree. Here's the new tree because I changed the file. This has a parent, which was my previous commit. And then it also has an author, a committer, and now the commit message. I'm going to switch over to another repo here. I'll go to the Flocks repo and find a merge commit here just to show what that looks like. And you can see this commit has multiple parents. And that's because it's a merge commit, and it has typically a merge has a first parent and a second parent, which is logically the branch you're merging into and the branch you are merging. You can also have esoteric commits with many parents if you do, say, an octopus merge, which is fun, but I don't know any other reason to do it. You will also see this commit happens to have a GPG signature. I wanted to demonstrate that, but I don't have GPG set up. So, and then a commit message. So similar concept, multiple parents. And we'll move on.
All right. Thank you, Nick. Also, the reason why I have to stand awkwardly here is because this talk is recorded, and otherwise I'm out of frame, just for context. All right, so we talked about commits, and we now learn that commits reference their parent commits. They can have 0 to many parent commits. But we also saw something else, and that this commit pointed to something that looked following way. It was a tree. And a tree is the second object that we're going to talk about. Trees are referenced by commits, and they describe the content of directory. And this is basically the way I see it. Commits, trees are actually they just document the structure of a certain directory. They can point to other trees, like subdirectories, or files. So this is what they contain. Files and their names. Those files could be other trees. Right. And another special thing is every commit that you make, I know we're talking about trees, but every commit that you make points to one tree, and that tree is the root of your directory. And from there, depending on how many subdirectories you have, those make up other trees. That's all.
Hey, it stayed put. This is great. Okay, so we will go back to the commit we had. We'll get cat file. I can also refer to it as head or main. And I have a tree here. So I can do the same thing. I can get cat file -t, and it says it's a tree. That's what we expected. I can do -p to pretty print it. And, oh, that wasn't the repo I wanted to do that in, but this is a great example. Here we go. This is open source. We can talk about it. This is Flux. So here we have a tree, and this tree has a list of file entries. This is very equivalent to what you would get if you did ls on the working tree of the repository. It has some files that have hashes. These are blobs. Again, you might imagine what's coming next. And a file mode. And then it has some subdirectories, which are also trees. So trees can reference trees. You might wonder, as I did, if you create a new repository and you make a commit that has no content, is that a tree without any contents or a commit without any tree? I don't know if anyone else wonders that, but the answer, it turns out, because I had to test it, is you get a commit, the commit always has a tree, the tree has nothing in it. So I will get back to main here, where it meant to be. I'll look at the tree for this, our slightly smaller tree. So you can see this tree has a single file, and it has a single blob, and we will I think that's all I wanted to say about that. We will talk about blobs in a moment.
All right. So this is the model that we're working with now, right? We know commits point to trees. There can be many, many trees. And at the end of the day, trees point to another object, which Nick already mentioned, are blobs. And this is where the content of the files live. That's all it is. Blobs are content of files, but not their names. This is very important because those two concepts are split in Git. The names of files or directories go to trees, and the contents go into blobs. Blob also has a hash, which is calculated from their content. And as you can imagine, it has a reason why it does this.
This is going to go better now that I remembered to get my notes out of my bag. So this is a blob, as we said. We can get cat file that blob. All right, any guesses what this is going to say when I ask it what type that object is? Yeah. Not a trick question. All right, and then I can cat file -p, and it's the content of a file, just like you would expect. I can... Trying to think of how best to show this. So this was my most recent commit, where the content of that is SCaLE with that capital A. So I also can look at the previous commit. The tilde means parent. previous commit parent, and find what the tree there was called. We can cat file that tree, and we see that it has a different blob for that same file name. And if we look at that blob, hello scale with the lowercase a. The other thing that we can do is we can copy that to, actually I'm going to move that file, test.txt, to SCaLE capitalized. And I'm going to copy SCaLE capitalized to SCaLE lowercase. And I'm going to change SCaLE lowercase back to a lowercase a, so we can see what happens. And I will add all of those files, commit them, and now we have yet another commit that has yet another tree. Things are kind of going off the screen. But you can see, oh, I didn't actually remove test.txt. I moved it on my file system, but I didn't commit that change, so it's actually still an outstanding change. I only added the other files. But so that actually works out perfectly, because you can see test.txt, well, I deleted it. Yes. Test.txt and SCaLE capitalized both have the same content, and so they are the same blob. They're the same exact object to Git, despite the fact that they have different file names. So the moving it around, Git doesn't care about that at all. And this SCaLE lowercase is the same blob that I had in one of my previous commits. So the same commit, the same file content. That blob can appear, reappear, disappear, be copied. If I create a directory and I copy those files into that directory, I can add that, commit, again, my great commit messages. Look at this commit and its tree. We can see that that directory is itself a tree. And so I now have a tree that contains a tree. And if I look at the tree that's inside the tree, it has the same blobs that are in the parent. So the same objects. So those objects are actually stored on disk in their own files in the .git directory under the objects subdirectory, right where you might expect to find them. They are broken up by the first two characters of the hash for reasons that we will get into in a little bit when we talk about this pack directory and what it does. These objects, so I had this, say this SCaLE lowercase file, that is d2 that, thank you tab complete, and I can actually cat that file and see that it is a bunch of binary data. And that's because these files are stored compressed. So if I can use pigz, which will decompress them, and see that this contains the word blob, and then 13, which is the length of the content, and then the content. So there's nothing secretive or magical happening here. We have a blob, it says blob, and then the blob, and then it's compressed and stored in a file. We can look at, where was that tree name? We can look at trees the same way. Trees are also stored as objects. I need to put that slash in. This one's a little more complicated, and this is because these are hashes of other, actually this is the hash, and then this is the file mode. But it's effectively, the slightly abbreviated version of what we get when we cat file that file, or git cat file that file, which is, it has several files with a mode and a blob. It's just here the hash is not stored as a hex string. The last thing is that we can look at, was there a question? Yes.
Are the hashes deterministic or are they matched?
The hash is deterministic. This is the SHA-1 hash of the word blob 13 hello SCaLE.
A new object and it was named blob, it would have the same hash in there. It
Yeah, so there's actually a command that you can run. I might run into new line versus not new line problems here, but you can pipe to git hash object, and it will do the work of hashing the object. You can pass -w, and it will actually write it into the store if you want to create arbitrary objects in your store. If we have time, we can look into how to construct a commit from the ground up without using git commit. The other thing is if I take the word blob and then 13, and I pipe to SHA-1 sum, it doesn't work, see? I forget if it's hashed and then compressed or compressed and then hashed. I might be missing that, but anyhow. Yes?
So, the question that's always come up is, what about collisions in the SHA-1 hash?
Yeah. If you're worried about collisions in the SHA-1 hash, the SHA-256 hash is also supported, and there's, I think, just a config setting you can set to do this. I recall some article from, say, 20 years ago about how, I think it was from Joel Spolsky, about how the odds of a hash collision in your Git repository are lower than the odds of your entire development team being eaten in simultaneous
about that. I think in 2020, I think it was Google and some university in, I don't know, Scandinavia. They actually managed to calculate, to create a collision. And this stirred some discussion, but basically Nick already mentioned the solution, SHA-200.
256, yeah, which should get us by for a little while until that's broken or quantum computers or whatever. You say that again? Yes, thank you. That is exactly correct. I believe I can do \0. And now I don't want the -n? No. -en. -e. There we go. Echoed. See, it's easy. But yeah, so this is the format of the blob. It's the word blob, the length of the content, a null terminator, and then the content. And that is SHA-1 summed, and then it's stored compressed. But this is the content of the blob. And if you're really careful, you could do the same thing for a tree. A lot harder because, again, you've got the binary representation of the SHA-1 sum. I tried to do this and started getting myself twisted with byte ordering and things. So, but that's how objects are stored. Back to you.
I'm not sure. I think back to you, Nick.
Back to me.
Yeah.
Are we talking about blobs?
Oh, no, we're talking about tags.
Back to you.
Yeah, back to me. So we talked about commits. We talked about trees and blobs. And there's this fourth base object that we need to mention. We're not going to get into details. And it's a bit confusing, but still bear with me. So we're going to talk about tags. Tags are confusing in Git because there are actually, spoiler, there are actually two types of tags. Only one of them is an object, namely the annotated tag. So if your tag has a message or is maybe signed, Git automatically creates an object out of it. And it appends it points to the commit it was created from. That's it. That's in the graph. It cannot only point to commits, basically to any other object. So you can create an annotated tag and point it to a tree or a blob, or also a different tag. So you can have nested annotated tags for whichever weird reasons you might want to do that. So, yeah.
I have searched the internet far and wide for any explanation of why you would tag a tree or blob, and if anyone has suggestions, I would love to hear them. Yes. I heard I think I missed the verb. I heard you can tag a blob and tree something GPG key.
Yeah, so in the Git project, they actually have a tag that points to the maintainer's GPG key.
Ah, fantastic. So you can store the GPG keys in the repository tagged, but not committed to the working tree. Yeah, there's a great example. That's a lot more useful than what we're about to do. So I think this project is ready to go. So I'm going to tag it 1.0. And I will, actually, for clarity's sake, I'm not going to make my message 1.0.0. So I have a tag. Unfortunately, git tag doesn't tell you the hash of the tag that it just made. So I will git show, which also doesn't show you. Okay, I will git cat file 1.0.0. This is a spoiler for something coming up. And this, it points to an object, and the object has a type, and that type is commit. So this is a tag that points to this commit. It has a tag associated with it. The tag object has a tag property. It has a tagger, that's me, and then it has a message. And here's why I use the different message, so we can distinguish the tag portion from the message portion. I can also, if I wish, say that, I think this is good enough that I'm ready to issue a feature release of the same exact content. So I'm going to go ahead and tag 1.0.0 as 1.1.0. That's really hard to type. You have created a nested tag. Yes, I have. And now I can get cat file 1.1.0. And we can see that that points to an object of type tag, which is this object, which was my other tag. I can kind of imagine a reason you might tag a tag, but tagging blobs and trees, well, aside from the one we established, I think the Linux kernel also has a tag of the original tree, like the original working tree has a tag separate from the commit, but it's a thing you can do. I think that's reason enough. Again, I would show a sign tag, but don't have GPG set up. I can go back over to the Flux repository, and hopefully we have sign tags in here. What was that? Git cat file .3.16. That's not one of them. I'm going to have a conversation with somebody. I believe that's it for tags. We've created a tag of a commit. We've tagged the tag. Well, I guess the last thing we can do is, again, we'll look at that first tag, and we can look at it on disk the same way that we looked at the other objects. We'll decrypt it on disk the same way that we did other objects. And you can see this one actually looks pretty similar to what we got when we pretty printed it, which is same thing with the word tag, 143 bytes, a null byte, and then object type tag tagger, which has me feeling like I didn't do this for a commit. So let's go ahead and get the commit and just show that as well. Here again, commit, 226, null byte, then the tree, the parent, the author, and so on. So.
Cool, thank you, Nick. I think now it's you.
Me. So that's the object model for Git. We've covered commits, trees, blobs, tags. That's all of the data that makes up your repository. But when you're actually working in the repository, there's a lot of additional state that Git is keeping track of to make a lot of the what we call porcelain commands work. Git, some of you may have heard that Git is sort of somewhat divided into plumbing and porcelain, where the plumbing are the low-level commands that tend to interact with these objects, and the porcelain commands are the things that a human interacts with. And so there's a lot of additional logic that is implemented at the porcelain level for things like branches. We didn't say anything about branches. I'm about to. I guess I can control this myself. So the first thing we'll talk about are refs. Refs live in the .git directory under refs, and there are a lot of kinds of refs. They are simply a meaningful name to a commit. You'll notice that I used some refs implicitly in what I was doing. When I talked about main, I talked about 1.0.0. But for the most part, commits they're identified by hash, and other objects are identified by hash. A ref is a way of giving a human meaningful name like main or my feature branch to a commit. There are several types of refs. Heads represent branches. Remotes are the conventional way of mapping remote refs to local refs, which is something that we'll talk about when we get to collaboration. There are tags. Some types of refs are tags. There's a special stash ref that implements the git stash command. There's a notes subdirectory of refs for the git notes command, and many more for all the various used by various utility functions and porcelain. In addition to refs, there is a special file called head. .git/head is a symbolic reference, which is a reference that refers to another reference. The content of head is a ref. Or it can be a commit directly, in which case you are in what Git calls a detached head state. If you've ever seen that, that's what that means, is that your head is not pointing to a ref, typically a branch, but it's pointing directly to a commit. So when I mentioned some of the porcelain commands, taking advantage of this, git commit, one of the things that it does is it creates a new commit, which has as its parent your previous commit, and then it moves the branch ref, the ref that corresponds to that branch, refs, heads, / whatever branch, to point to that new commit. So we mentioned earlier that the conception is that a branch is a list of commits, which is not entirely true. A commit is always part of a tree of commits, or a tree of commits, yes. But like I said, directed acyclic graph of commits. But the commit itself, sorry, not the commit, the branch only refers to one particular commit, and there's magic that moves that branch along as commits are added on top of it. The last part of the sort of local repo state is the index. This is another file that's stored in .git/index, and it represents Git's view of the work tree. I think I said working tree here. That is not quite correct. Working tree and work tree are slightly different concepts. If you want to know that, look at Git help glossary, which will define that. The working tree is the files actually on disk. The work tree is this thing that I'm describing here, which has refs and a head and an index and a working tree. But so this is Git's understanding of which files exist in the repo right now, which things are checked out. That's different than what is on the most recent commit or what is actually on disk. The most common place this happens is that it stores files that are staged to be committed. When you git add a file, that adds it to the index. If you then go change that file on disk, which we can do in a moment here, you'll see that you have changes committed and changes uncommitted to the same file. So you have 3 different versions of that file that Git is aware of. And it's also used to cache file system state for the entire current work tree so that operations like git status can easily tell, if you have 100,000 files, which ones have changed. I believe that goes to demo. So in this repository, I will start by checking out my head, or not checking out, that's a Git term, by looking at my Git head. So this says ref is refs/heads/main. And we can look at refs. You'll see I have refs heads and refs tags. Refs heads, I have refs heads main. That is my branch. And I can point that, cat it. It is a commit. And if I git show, that is the commit that I am currently on. If I look at the commit graph, this is the commit I'm on, this is its parent, its grandparent, and my initial commit. And here's a bunch of aliases for that commit. These are, again, refs are different names for a commit. This is I have a format here set that prints these aliases. But you see I have head. Head is this commit because it's main. It also has a tag called 1.1.0 and a tag called 1.0.0. I can move that content. So I will cat that file again. I can, an easy way is reset on head, and this takes me back a commit. And then I can reset back to that commit. I can also git update ref to this commit. That's more of a plumbing command. I may have swapped the order of those arguments. Ref name it. All right, well, I didn't test that part before I did this. So you can use git update ref somehow to move the ref pointer. But so my head is main, and main is this commit. That's effectively where we're at. The other kind of refs that you have are tags. Now, we mentioned earlier that there are two kinds of tags. There are annotated tags and lightweight tags. Lightweight tags are just a ref. This is quite literally a file whose contents are a commit hash. That is not one of my commits. Right, yes. I will try making an unannotated tag on main here, 1.2.0. Oh, well now my update ref, I think, has caused some trouble for me. But if I cat 1.2.0, now it points at this commit. Oh, I've really messed some things up. Update ref. We'll set that back. Let me just delete that. Cool. Very good. Okay, well now it's unambiguous, or it's ambiguous, but I think it's ambiguously the same thing twice. Two ways to get to the same name. As Tongi mentioned earlier, the caveat here is that Git is enormous and complex, and we've been learning it for a long time for this talk, and every time we learn one feature, we learn about two more related features. So I've managed to confuse myself. That's where we're at. Next year, I'll learn what I just did and explain that. But I can talk about the tag here that I've created. So 1.2.0 points at this commit. Now 1.1.0 doesn't point at a commit. And that's because when you use git tag to create an annotated tag, what you get is both an annotated tag, which, reminder, is an object that references another object. In our case, 1.0.0, we'll look at, references a commit. But the lightweight tag here, the ref, actually references the tag object. So you wind up with a lightweight tag and an annotated tag, where the lightweight tag points at the annotated tag. And the reason for that is that if I didn't have this ref, the canonical name for my tag is actually 5F87167, what have you. I still want a friendly name for it. So it has the tag info inside of it, but it also then is referred to by this name externally. And so it's kind of tags all the way down that way. The other thing here was the index. So I can run git status, which will compare the current commit, head, to my current working tree and to the index, and find if any of those things are different. In this case, they aren't, so it says nothing to commit. Now I still have that test.txt file, so I'm going to add some content to it. And now I can run git status, and it says changes not staged for commit. I've modified test.txt. If I now add that, I can see that it's now a change to be committed. It's modified. It's in the index. I can make further changes to that file, continue adding hellos, and I now have a change to be committed and a change not staged for commit. And to look at that, I can see git diff will show changes that are not staged. This is actually diffing against my staged content and showing me the unstaged version. If I do -- can can I do staged? I usually do cached. You can do dash dash cached or dash dash staged. The index was originally called the cache. And this now shows my staged change versus the original copy. So I have 3 different versions of that file here. One thing that git add does, let me see if I can see, here we go, is it actually creates an object for any of those outstanding files. And so I actually can cat file this object. It exists in my repository before I've committed that content. The object is present. So the index is actually a list of pointers to objects, as I understand it. Again, this one is a little over my head right now. I will go learn more. So this object is created. If I say throw away that change, reset, right, it's now no longer staged, but that object still exists. And it will eventually be garbage collected if it's never committed. I'm not sure how much we're going to talk about garbage collection. I think a little bit. We got. Yeah, we'll get there. So that's just a little bit about the index. And again, it's also used if you run git status on a large repository. The index is responsible for tracking the previous last known state of all of those files to see quickly whether they've changed by statting the whole tree. I believe that's it for this demo section.
All right.
Is this also me?
Yeah, so now we come to the point where it all should make sense. And I would like to invite you all to look at this graph. And so you remember in the beginning, I showed you like a picture with commits and 2 branches. So what you're seeing now is a more accurate representation of what a Git graph actually looks like. And oftentimes in those diagrams, believe me, trust me, they were correct, but they were kind of hiding the lower part, like, or even the upper, some parts of the graph. It was a different representation. But what is important to know that these things are objects. And if we visualize the references from one object to another, we receive a graph. And so what I wanted to point out here is actually, remember in the beginning, I mentioned how a commit actually is a snapshot of all of the files, all of the directories at a given point in time. And so as you can see here, this new added commit actually only adds this one blob. And so this is the change that got updated. But this tree, so this directory, also had a different subfolder, which contents got updated in the commit before. And so our new commit doesn't recreate everything that it was that is there. It only actually adds the new objects, the objects of the change, but also by reference includes the state of the entire repository. And I thought it was a very helpful mental model that kind of made it click. As Nick already mentioned at some point, just for the record, a Git graph is a directed acyclic graph, also known as a DAG for those of you into graph theory. So there you go. We also looked a lot at objects, right? Those things that are hashed and there are directories that begin with their hash letters. So when we talk about that, we talk about loose objects. So all of those things that Nick catted at are actually loose objects. And those objects are points in the graph, right? Talked about it. But as you can imagine, if we keep adding more and more files onto our system, if we introduce a change, so right, if we were just to change one single line in a file, it would create an entire blob. That becomes inefficient very fast, right? Because many files, well, first of all, they take up a lot of space, and they also take a lot of time to process if there are many of them. And so what we want to talk about now is So we talked about this graph, and now we want to talk about its physical representation on disk. So the loose objects is one option, and there's a second option that is kind of an optimization of that, and those are pack files. We're going to look at pack files in the following demo, but some of you might have already encountered the pack directory in your .git objects. And basically, if Git decides that there are too many loose objects, it starts packing them. And one pack consists of several files. Very quick, because it's kind of already, there's a lot to cover, so very, very quick. There is a .pack file, which is just the binary data. That's just data, straight, and nothing else. There's an index file that actually, where Git stores pointers and references in that archive file, basically. And if your pack is very, very large and contains many objects, there might be that it might doesn't have to be this way, but it might also create a .rev file, which is a reverse index of that pack. Again, this is where things get really interesting, but also very complicated.
So yeah, we mentioned earlier that commits don't represent diffs, and that diffs are just sort of implied by the comparison of two trees or blobs. But if you've used Git a little bit, you'll see when you do a pull, resolving deltas. What are those deltas if they're not diffs that are my commits? Well, when packing objects into a pack file, Git uses an algorithm it calls delta compression. This is a little bit obscure, but the idea is effectively that it groups objects by type. So commits are grouped with commits, and trees are grouped with trees, and blobs are grouped with blobs. And then it orders them according to recency. So the things that are reachable from these sort of heads, we have those head refs, the tips of your branches. Those come first. So the idea is that it will try to store the most recently used or most currently active contents together in the file for locality, and also whole, rather than breaking them out and having to apply deltas to get at the most recent state of the repository. It then orders them by size, sort of under the idea that files in a code repo just grow over time, and so that if you have a file that is, say, it's not by lines, but if you have a file that's 10 lines and then 12 lines and then 14 lines, they probably came in that order. And it's not a very complex algorithm. It orders them that way, and then for each object, it checks the previous 10 objects it packed. Again, it groups them by base name. So again, we said a blob or tree can have multiple file names, but it just, whichever one it sees first being from the most recent state, it uses that name so that it will try to keep the history of a single file together, again, under the assumption that it will tend to change over time, or tend to be the most similar to itself than to any other file, ordered by recency and size. And so it looks at the last 10 things that it packed, says, what's the delta that I would have to apply to that object to get my new object that I'm trying to pack? If that delta is smaller than the object itself, then it will store it as a delta. So the basic thing there is that if you have the current version of a file, and that it will store that in the pack file. And then the last commits version of that file that was, 2 lines of code less, it will say, hey, I don't have to store this whole file. I can say that this file is that file minus these 2 lines. And a lot of the time, it will be right. It will find that one of those 10 is more efficient to store. I'm not sure if it's still 10. Actually, the information we got is the best we could find is a doc in the Git repo that is a transcript of an IRC conversation between Linus and some people who wanted to know how it worked from 2006. So the details could have changed. But this is roughly the idea, is let's just take all of our objects, order them in a way that puts like near like, and then see if any of the objects nearby are similar. And if they are, then we'll store that. if you have two completely different files, the delta that you have to apply to the first file to make it equal to the second file is larger than the second file itself, in which case it decides, I'll just store the second file. I believe that is everything we have there. Yeah. And there's a demo. Yeah. I'll give a really quick demo of this one. So I will run git gc. Git gc is the command that occasionally runs. There's a whole maintenance process, and sometimes it will decide that it needs to run gc. I believe it's typically like if you've got more than 6,700 loose objects by default. And you can see that all of my objects are gone. That's the magic here. And they're now in a pack file. They're now in a pack file. They're actually in a couple of pack files. But I can run this helpful command, git verify pack -- verbose, and that will go and verify. This is actually meant to verify that the pack is intact, but what it does is it prints everything it sees in the pack. So you can see we have a commit, we have a tag, another tag, a commit, a commit, a commit, and then down here we have a tree, and this second tree on the right, this is a delta storage. This is saying that this tree is stored as a delta applied to this tree. All of the numbers here are sizes and offsets within the pack file. Because again, as Tanya said, the pack file is just a blob of binary data, and then the index file is a bunch of pointers into it for where to find that data. So if we cat file, the objects still exist logically. I can still cat file them the same way that I could before. They just are being read out of the pack now rather than being read as objects on disk. So you can see that this second tree here was the same as this first tree, but minus this directory. So it decided that I may as well just store that delta. And because this is the current state of my tree, that's the one that gets stored whole. So it stored this one, and then when it got to this one, it said, I can make that equivalent to this. I would show there's a very fun command. If you move the pack file out of the Git repo, then you can run git unpack objects, which will take the pack and turn them back into loose objects. Unfortunately, I don't think we have time for that. Try it at home.
But maybe don't try it at home at your real work project. Create a, temp
Yeah, don't do what I did.
All right. We have prepared some bonus content just because we anticipated that we'll probably not get into every detail, but those pack files are super interesting because they are actually at the core of how and why Git, fetch, or pull, and push are so fast and efficient. Well, fast, but I think it's kind of impressive still. So, you all know remotes. We're not going to talk about it. So basically, Git has two protocols to transport your data. And the Smart Git protocol, well, basically both of them, actually. Yeah, I'm confusing that. Basically, both of them figure out which objects you need to have. The client requests, or the client needs to send to the server. Doesn't matter. And it ships the change in form of these pack files. So super, super compressed. And then the other respective side unpacks them and appends to their Git tree. That's kind of the TLDR on that. So today, I hope y'all got a small overview on the Git object model, how the repo state looks like. You have a more accurate graph representation and know what pack files are. And now you know where to look up dumb and smart HTTP protocols. And here, I want to say thank you and for listening to us. And yeah, have fun Saturday.
Yeah, thank you.
Thank you so much. It's clear that an hour is not enough to unpack Git. So next time, reserve a 2-hour slot, and we'll be here to listen. So unfortunately, we don't have time for questions, but I invite you all to continue this conversation, I suppose, outside of this room. Thank you so much. Come to the Flux booth.
Okay. Can you hear me? Sweet. It's always you. Like, it's always your friends that like being at art. Okay. Okay, sweet. I'll turn.
Hello, everyone. It's the last session of the day, but I'm super excited to be here, and I hope you're all also excited to hear about Barbie's journey as CI/CD tale of transformation. Take it away.
Can everyone hear me? Sweet. Okay, so I saw the Barbie movie, and it was awesome. And I decided it would be a great way to use it to teach girls about DevOps for Grace Hopper. But taking it to scale, everybody's like a DevOps engineer, so I was like, we're gonna have to change this up. So I decided to make it more of a cautionary tale about the ways that things go wrong when we don't pay attention to the human aspect and to the way that we incorporate DevOps kind of methodology and how we make that work at scale. So this is more of the re-architecting DevOps Barbie. So before we get there, I'll tell you a little bit about me. So currently a product manager at Microsoft. Hi, boss. Used to be an SDE on the Credo team at AWS. I do a podcast with our lovely friend in the front seat. The chicken only shows up for conferences, apparently, but many other things show up for our podcast. Our podcast is Fork Around and Find Out. We used to ship it together. I'm on the education board for Millspouse Coders. I really enjoy teaching women how to code and helping women to find careers in technology. I have 3 feral but very cute children and a college student, so if you see him around, help him get an internship or a job so I can stop paying for all his stuff. I have a slight coffee obsession that isn't obvious from all of my... Wow, Justin? Did you see... Okay, all my social media handles may be with enough coffee because I think I can take over the world if we caffeinate me enough. And tacos are life. So, the beginning of the Barbie movie starts, and Barbie lives in this perfect world where the patriarchy doesn't exist, feminism is amazing, and you build stuff and it works the first time and there's no bugs. Has anyone experienced building anything in that type of world? Because I haven't. So Barbie gets this idea, and she's going to build a startup with her friends, right? So she's got this great idea. They're going to make this product. They set out on this wonderful journey where you build stuff once. You design it, you get your requirements, and then it just magically works forever because maintaining software isn't hard or anything, right? So you've built, you've tested it, you've gone and stayed up all the long nights, and you're ready to release. People start using it, funding starts rolling in, and everything's great. All of a sudden, humans are using your product, and they start using it in all the wrong ways that you did not attend. You came up with all the edge cases that you can expect in it, and somebody starts using it in ways that make absolutely no sense, and they found all the edge cases you didn't. They're asking for new features. We've got bugs and regressions, and now it's Barbie's job to get all of this out while still having a good uptime and making it highly available. Anybody ever felt like this at work? A little bit. So, she's not dead. She's just having a little bit of an existential crisis because she's now learned what it feels like to maintain software. She's trying to patch bugs, get them out as fast as possible, and do a manual release process. Instead of using an iterative release process that has a feedback loop. We'll never know what that's called. Funding rolls in and she thinks, okay, we'll hire a bunch more engineers and everything will fix itself, right? Even with version control, hiring a bunch more engineers and hoping that they can all work together and onboard the same, and that you'll be able to not incur huge breaking changes with no rollbacks and not knowing where you hit your road bumps, Barbie is still struggling. Now the engineers are pissed because everybody's code is colliding. We've got merge conflicts. On-call sucks. And everybody is very unhappy. They go talk to Weird Barbie. Weird Barbie's like, look, you can have perfect. You can just decide that you're going to ignore real life and building things. Or you can go to the real world and figure it out. Barbie tries to pick perfect, but Weird Barbie's like, dude, that's not how this works. Sorry, you have to go to the real world. She tells her about these really cool concepts like agile, DevOps, automating all the boring stuff. Barbie's like, okay, fine. If that's going to solve the problems, keep the engineers happy, and keep the startup afloat, I'll go to the real world. Ken apparently invites himself, because he does that to everything, and all he does is beach. They venture off into the real world to figure out what agile, DevOps, and iterative development is like. So this talk isn't really about CI/CD necessarily, because I think everyone in this room knows what DevOps is. But there has to be more of, you can't just fix technology, right? There's human aspects to it, and we have to make it better for humans to build it. We have to make it easier to onboard people and to have everybody have a seat at the table to build good software. And I think sometimes, especially now in the current climate, it's just be as technical as possible when people skills are a little important with engineering being a team sport. So Barbie starts doing a lot of research and testing with automation. She gets a lot of alarms and pages. Implementing things can be kind of hard. It sounds great online in Google until you have to do it in real life, and then it can be like a little crazy and feel like you're on a ride. Barbie calls a senior engineer she used to work with at her old company, and she's like, dude, I thought it was supposed to get better. That's the face the engineer gave her. She's like, I've got some secrets for you. You can have all the automation and DevOps you want, but if you're not getting a good feedback loop and you're not listening to everybody's perspectives, also you have no observability or monitoring. How do you think you're going to find your problems and then work to improve them? So she goes back to the drawing board. She talks to her council of Barbies. Lawyer Barbie talks about how you can both be emotional and logical, and it doesn't diminish your power, right? One of the most important things that we have going for us in tech is the human aspect. Has anybody seen anything on the news that was a technical flop that we all knew was a bad idea, and because one person that didn't have any friends that looked different than them weren't there to say, this is a bad idea? Like, a lot. Sometimes having someone to just be very honest and having a safe environment to say, dude, don't build that, please, is really important. So apparently, Ken and Barbie had very different views of going to the real world. Barbie decided she really likes test-driven development and DevOps. Ken came back with like Chad-driven development and being a 10x engineer. We don't know where this is going to go wrong at all. Ken's decided he knows how everything works. He built everything. There's no need for documentation. What do you mean a customer feedback loop? He doesn't care about the customers like it. He wants to build cool things because that's what engineers do. He doesn't care about educating or growing junior developers. He's going to do it all by himself. He doesn't need other people. I intentionally left out my favorite aspect of building things. You can have the coolest, best distribution operating system product, but if you forget to secure it, nobody's going to use it. So, we didn't talk about, Barbie didn't think about least privileges or security or any of that. And Ken takes over the Barbie dream house and makes it Ken's Mojo Dojo Casa. So now Barbie not only has a mutiny going on, she's got security problems, and she's got to deal with that. Okay, so Barbie calls DevOps Barbie, Security Barbie, CISO Barbie, Architect Barbie, and they come up with a plan. First of all, they kill Ken's credentials, kick him out of all of the infrastructure. They start building changes to artifacts and make sure everything undergoes constant and frequent automated testing. So they incentivize documentation, education, and mentorship programs while automating all the boring stuff and making testing a part of development. They also take into consideration cost, because while the startup's doing really good and it's flush with cash, if you save money, you save people, especially in this current market. Ken decides being a malicious actor is not for him. He's really disappointed that there's not as many horses as he thought in the patriarchy, and he's lost interest. So, moral of the story is, when you give people diverse perspectives and a safe place, and you take everybody's opinion and you take their superpowers that they all bring to the table, some people are not the fastest developers, some people are maybe really good at front end or really good at back end or whatever, but everybody is teachable. And well, not everybody, we all know that one dude at work, but for the most part. But it's more about investing and teaching people and getting people on the same page, right? So, giving people the freedom to fail, making sure that software maintenance and collaboration become expected, making sure you have a place to roll back when experimenting, efficient software development, and making sure that you actually care about the people that are using your stuff, so you actually make competitive software. Because if you don't secure it and if you don't build it well and listen to your customers, your competitors will do it. Automation helps with less human error, but you need good humans to actually write the automation first. That's my talk.
Thank you so much. Comments, questions?
We all know the first movie did very well, right? It was a blockbuster. So you know that they're going to go for a sequel. So can you predict what's going to happen in the sequel at all? Any ideas?
Work? Do I have to move my hair? Okay, cool. So I think it's gonna be a megla tech millionaire that doesn't go to therapy, and he takes over a whole government, and then the Barbies have to save it. Cause that would be such a good story, right? I mean, it would be kind of unbelievable, but where would we get it? And then they'll just do a lot. Can you imagine? I can give a whole security talk about not securing databases. We could talk about just giving everyone access to all of your personal identifiable information and not, right? But that would be just too unbelievable, and we would it would be a little far-fetched though. totally. Any other questions? Thank you guys for all coming. This is kind of a silly talk.
Thank the
so.
speaker again.